The way in which factories turn potatoes into Pringles, Doritos, and Walker's crisps is so impressive, these brands don't want you to know how they do it. One slight shift in moisture or seasoning flow can turn a batch stale in the matter of seconds. In this video, we go inside the lines from raw ingredients to high-speed frying, uncovering the secret ways these brands use to make their product near perfect. Pringles are manufactured as a formed potato and starch dough that is rolled into a thin sheet, stamped into a precise saddle shape, cooked to low moisture for crispness, seasoned, then stacked and packed so every crisp fits the same tube geometry. The entire process is built around the final stack because the product must be dimensionally consistent to nest cleanly. That means thickness, curvature, and shrink must be controlled more tightly than in sliced chips. The line, therefore, treats dough rheology and forming temperature as primary controls, not just cooking time. The last operation before packaging is stacking. After cooking and seasoning, the crisps move into orienting channels that flip them into a single consistent face direction. Orienters rely on the saddle shape to guide each crisp into the correct orientation. Pieces that are too flat, too curled, or warped will not travel correctly and will jam. For that reason, dimensional inspection and curvature control are enforced upstream. Once oriented, crisps enter a stacker that nests them into a column. Stack height is counted or measured by length sensors, so each tube receives a consistent number or mass. The stack is pushed into a tube, and the tube is sealed with a cap and foil or membrane, depending on the packaging design. Packaging is not passive. The tube protects the product from breakage and also provides a controlled headspace environment. The tube seal must be tight because moisture uptake softens the crisp. Barrier materials and sealing parameters are chosen to keep water vapor transmission low. Seasoning is applied immediately after cooking, while the surface still carries enough oil to act as an adhesive. Crisps pass through a rotating drum where fine seasoning powder is dosed by mass flow. Drum speed is tuned so crisps tumble without snapping. Because Pringles are uniform, seasoning distribution can be very consistent if the oil film and residence time are stable. Excess seasoning is controlled because too much loose powder collects at the bottom of the tube and affects consumer perception. Cooking creates both crispness and a stable shape. Unlike sliced chips that float in oil, Pringles are often fried on a conveyor or baked then fried depending on the process variant. The key requirement is that moisture is reduced to a low end point while the crisp is held in its saddle form. If the shape is not held, the sheet will shrink unpredictably and curl. Crisps are carried through hot oil on a belt or between forming elements that maintain curvature. Oil temperature is held tightly because it controls how quickly water leaves and how the surface sets. If oil is too cool, the crisp stays longer, absorbs more oil, and can become heavy. If oil is too hot, the surface sets before the interior dries evenly, leading to blistering or brittle weak spots. Residence time is synchronized with line speed and thickness, so the final moisture endpoint is reached consistently. Oil management remains critical. Crumbs and fines are filtered out because they burn and darken oil, changing heat transfer and flavor. Oil circulation keeps temperature uniform across the fryer width. Consistent oil quality helps maintain consistent color and prevents off notes. After frying, excess surface oil is removed with drains and air knives, so the seasoning step begins with a controlled oil film rather than variable pooling. Before frying, the product is formed mechanically from a dough sheet. The sheet is created from a blended dry base and a controlled water addition. The dry base typically includes potato flakes, potato granules, and starches that set structure. Flour or other binders can be included to tune elasticity. Dry ingredients are screened to remove lumps because lumps create weak spots that tear during sheeting and show as holes in the crisp. Water and any minor liquid ingredients are metered into a mixer where the dry base hydrates and becomes a cohesive dough. Mixing intensity is controlled because too much work develops elasticity that causes snapback and warping when stamped. Too little work leaves dry pockets that crumble and tear. The dough must be plastic enough to roll into a thin sheet without cracking, but not sticky enough to smear on rollers. Dough temperature is controlled because it drives viscosity. Warmer dough becomes softer and can stick to rollers. Colder dough becomes stiff and cracks at the sheet edges. The line aims for a narrow temperature band and uses jacketed mixers or conditioned rooms to keep that band stable. Resting time can be used after mixing to allow moisture to distribute evenly, which improves sheet uniformity. Sheeting is done through roller mills that progressively reduce thickness. The dough passes through a series of gaps rather than one large reduction. This prevents tearing and keeps thickness uniform across the width. Gauge rollers at the end set the final sheet thickness. Thickness control is one of the most important variables because thickness determines final crisp strength and how it nests in a stack. Even small thickness differences change curvature behavior during forming and change cook time in the fryer. The sheet then enters a stamping and forming section. A cutter punches oval blanks from the sheet. Scrap around the ovals is collected and returned to the dough system at controlled ratios. Rework ratio is controlled because repeated rolling changes hydration and can increase fines, affecting dough behavior. The oval blanks are transferred immediately into forming molds that create the saddle geometry. Forming molds are paired surfaces that press the blank into a curved shape. The blank is held in this geometry as it enters the cooking stage or a pre-dry stage. Holding shape during early heating is critical because shrink begins as moisture moves and starch sets. If the blank is not constrained, it shrinks unevenly and warps. Many lines use a pre-dry or bake step before frying. A brief bake removes some moisture and sets the surface so the blank can move into oil with less deformation. Baking also reduces the time in oil, which can help control oil pickup. The bake profile is tuned so it stiffens the shape without fully drying the piece. The piece must still be pliable enough to conform to the mold and avoid cracking. When the molded pieces enter the fryer, they are supported so they do not float and lose curvature. Belts and mold carriers maintain spacing and prevent contact between pieces. As moisture leaves, the structure becomes rigid. The exit condition is a crisp that is dry enough to snap, uniform enough to stack, and strong enough to survive handling. After frying, the pieces are cooled briefly to stabilize the structure before seasoning. Cooling also reduces surface volatility and helps the oil film set. Pieces then enter the seasoning drum. The drum uses gentle tumbling to distribute powder. Seasoning rate is synchronized with product throughput, and drum residence time ensures coverage without overhandling. Following seasoning, pieces are inspected and sorted. Vision systems can detect warped or broken pieces that would jam stackers. Out-of-shape pieces are rejected. This sorting step is important because stacking systems require consistent geometry to nest smoothly. Even a small number of warped pieces can create stack misalignment and tube filling issues. The oriented pieces then enter the stacker. Orientation channels guide each crisp into the same direction. The stacker nests pieces into a column and transfers the column into a tube. Tube filling is synchronized so stacks do not collide and break. Once in the tube, the product is protected from crushing and from moisture ingress. The tube is sealed, coated, and then cased. Doritos are manufactured by turning corn into a cooked masa, converting that masa into thin sheets, cutting the sheets into triangles, frying to a controlled moisture endpoint, then applying seasoning through an oil film so each chip carries a dense, uniform flavor layer without clumping. The process is anchored around seasoning adhesion because Doritos carry far more powder per unit surface than plain chips. That means the chip must leave the fryer with the right surface oil level and the right dryness. Too much oil creates heavy seasoning pockets and greasy mouthfeel. Too little oil produces bald spots and uneven flavor. The factory therefore tunes frying, de-oiling, and seasoning drum conditions as a single linked system rather than independent steps. After frying, there are chips pass through drains and controlled agitation that remove free oil while leaving a thin adhesive film. Vibration and mesh conveyors let oil fall away. Air knives can strip surface oil selectively. The target is a consistent oil film thickness that supports seasoning pickup. From there, the chips enter a seasoning drum where powder is dosed by mass flow. Drum rotation rolls the chips so both sides see powder. The powder blend includes fine salt, acids, dairy solids, spices, and flavor compounds, and it must remain free-flowing to distribute evenly. The drum residence time is long enough for coverage, but short enough to avoid breaking chips into fines. Excess powder is minimized because loose powder settles in bags and contaminates seals. Packaging begins right after seasoning. Chips feed into multi-head weighers that portion weights by combining multiple hopper dumps. Gentle drop paths reduce breakage. Bags are formed from barrier films and are often nitrogen flushed to displace oxygen and create headspace that cushions chips. Seals are made with controlled heat and dwell so the bag closes without leaks. Moisture and oxygen barriers protect crispness and flavor stability over time. All of that downstream performance depends on how the chip was built upstream. Doritos start as corn that is converted into a dough called masa. The primary transformation is cooking corn kernels in an alkaline process. Whole corn is cooked in water containing a controlled amount of alkali. This step changes the kernel structure and helps loosen the hull. It also alters protein and starch behavior so the later dough forms correctly. Cook time and temperature are controlled because overcooking produces a sticky dough that sheets poorly. Undercooking produces a grainy dough that cracks. After cooking, the corn is steeped to complete hydration. Steeping time is controlled so water penetrates the kernel uniformly. The cooked kernels then go through washing to remove loosened hull material and to adjust surface chemistry. Wash intensity is controlled because too much washing can strip solids and change dough behavior. The washed kernels are then ground into masa using stone mills or modern grinders that produce a uniform particle size distribution. Grinding is tuned for sheetability and bite. If the grind is too coarse, the sheet will have weak points and tear during cutting and frying. If too fine, the dough becomes overly cohesive and can shrink unevenly. Water is added during grinding or immediately after to reach a target dough moisture. Moisture is the key variable that determines how easily the masa sheet forms and how it fries. The dough must be plastic enough to roll without cracking, but not so wet that it sticks to rollers and creates thickness variation. Masa mixing follows grinding. Mixing distributes moisture and stabilizes the dough. Resting can be used to let moisture equilibrate, which improves sheet uniformity. Dough temperature is also controlled because warm dough becomes sticky and cold dough cracks at edges. The system uses jacketed equipment or controlled ambient conditions to keep dough in a narrow temperature band. Sheeting converts masa into a continuous thin band. The dough passes through multiple roller gaps that gradually reduce thickness. Gradual reduction prevents tearing and keeps thickness uniform. The final gauge gap sets chip thickness. Thickness drives frying time and final crunch. It also drives how much seasoning can be carried because thicker chips have more structure and surface roughness. The sheet then enters cutting. Rotary cutters punch triangles at high speed. Cutter timing and alignment define triangle shape and minimize scrap. Scrap sheet around triangles is collected and reintroduced into the dough stream in controlled ratios. Rework ratios are limited because repeated rolling changes, hydration, and particle damage, which can increase fines and change sheet strength. Before frying, the triangles are conditioned. Some lines use an oven or pre-dryer to remove a portion of moisture and set surface structure. Pre-drying stabilizes shape and reduces time in oil, which can reduce oil pickup. The pre-dry profile is tuned so the triangle becomes firm enough to handle but still flexible enough not to crack. Frying is the main crispness forming step. Triangles enter hot oil and immediately release steam as surface water flashes. The steam creates pores and drives moisture out. As moisture drops, the structure rigidifies and the chip becomes brittle. Oil temperature is held tightly because it controls the rate of water removal and the degree of browning. Too cool yields oily, flexible chips and inconsistent seasoning adhesion. Too hot yields fragile chips that darken and break. Residence time is controlled by conveyor speed and chip bed depth. Bed depth must be shallow, so every chip sees similar oil contact and heat transfer. Oil circulation maintains uniform temperature across the fryer width and prevents cold spots. Filtration removes fines and crumbs that burn and darken the oil. Oil turnover keeps oil quality stable, so flavor and color remain consistent. After frying, chips pass through a color sorting system on many lines. Optical sensors detect overly dark chips or defective shapes and eject them. Sorting tightens visual consistency in the bag and removes chips that would taste more bitter from heavier browning. The fried chips then go through the de-oiling steps that were set up to support seasoning pickup. The factory treats de-oiling and seasoning as a coupled system. If the seasoning formula changes, the target oil film may change too. Fine powders require less oil to adhere evenly. Larger particle blends may need slightly more oil. The line adjusts drain time, vibration intensity, and air knife settings to land at the correct film. Seasoning powder handling is its own process because Doritos powders are complex blends that must remain free-flowing. Powders are blended in large mixers and screened to break clumps. Moisture control is critical because humidity causes caking. Feeders meter seasoning into the drum at a rate proportional to chip mass flow. The drum is designed to provide enough tumbling for even coating without creating breakage. Interior lifters lift chips and let them fall through a powder cloud, promoting coverage on both sides and edges. After seasoning, the chips are screened lightly to remove loose fines. This reduces dust in the bag and helps maintain seal integrity. Then the chips are weighed and bagged, flushed with gas, and sealed. Case packing stacks bags in a way that reduces crushing forces and keeps headspace intact, because the headspace acts as a cushion. Walker-style crisps are manufactured by engineering a thin potato slice into a dry, brittle matrix with a controlled surface oil film, then locking that texture in with fast packaging that blocks moisture and oxygen. The process is easiest to follow from the fryer exit because the fryer decides the final crunch and the exact oil level that seasoning needs in order to stick. As slices leave hot oil, they are still losing steam through their pores. If they are held too long without draining, oil can continue to migrate into those pores as internal pressure drops. The line therefore moves crisps immediately onto draining conveyors and vibration decks. Vibration shakes off free surface oil, while the crisp is still rigid enough to tolerate movement. Air knives can strip oil from curled edges and from the center dish area. The objective is not a completely dry surface. It is a consistent, thin oil film that supports seasoning and gives the correct mouthfeel. Seasoning is applied while that oil film is still warm and mobile. Crisps enter a rotating drum where seasoning powder is metered by mass flow to match crisp throughput. Drum internals lift and cascade crisps, so powder distributes across faces and edges. Drum speed is tuned to roll crisps without grinding them into fines. Too much agitation creates dust that collects in bags and contaminates seals. Too little agitation yields patchy coverage. For lightly salted crisps, the dosing rate is low and distribution must be especially uniform because any local salt cluster is obvious. For flavored crisps, the powder mix is more complex and often includes fine salt, acids, dairy solids, spices, and flavor carriers that need controlled humidity to remain free-flowing. After seasoning, crisps are screened to remove small fragments and fines created in slicing and frying. Removing fines improves bag appearance and reduces dust that can weaken seals. It also helps keep seasoning distribution predictable because fines carry disproportionate seasoning. Packaging is designed to preserve the crisp matrix that was created in the fryer. Multi-head weighers portion weights by combining multiple small hopper dumps. Drop paths are designed to reduce breakage. Bags are formed from barrier film and typically flushed with nitrogen to displace oxygen and create a cushioning headspace. The nitrogen headspace reduces oxidation and protects crisps from crushing. Heat seals close the bag. Seal temperature and dwell time are tuned so seals hold without wrinkles that would leak. Even small leaks allow moisture ingress, which softens crisps by raising water activity and plasticizing the starch matrix. The fryer performance that makes all of this work depends on what happened to the potato slice before it reached oil. Slices must enter the fryer separated with low surface starch and with minimal free water. If slices stick together, they cook unevenly and trap moisture. If surface starch remains, it forms a sticky film that encourages clumping and creates dark specks in oil. If surface water remains, it cools the oil locally and increases oil breakdown. That is why the pre-fry section is built around starch and water removal. Immediately after slicing, the slices fall into a flume or wash system that keeps them suspended and separated. Water flow and turbulence are tuned to strip off loose starch without tearing thin slices. Countercurrent wash systems can be used so cleaner water contacts cleaner slices near the exit. This reduces total water use while maintaining starch removal efficiency. After washing, slices are dewatered on vibrating screens and then passed under air knives. Dewatering is more important than it looks. A few extra grams of water per kilogram of slices can pull fryer temperature down and create a soft, oily crisp. Dewatering also reduces splatter and helps oil stay stable. The line targets a consistent surface dryness before the slices reach oil. Slicing itself is the origin of thickness consistency, and thickness consistency is the origin of uniform cook. Potatoes are fed into high-speed slicers, where rotating blades cut slices to a fixed thickness. Blade sharpness is critical. Sharp blades cut cleanly and preserve cell structure. Dull blades tear cells and create ragged edges that absorb more oil and generate more fragments. Blade condition is monitored by slice quality indicators like feathered edges and by mechanical signals like vibration and motor load. Blades are changed on schedule, so thickness and edge quality remain stable. Potato feed to the slicer is stabilized because potato size affects how the slicer loads and how slices land in the wash flume. Potatoes arrive in bulk and are graded by size. Oversized potatoes can overload slicer throats and cause thickness variation. Undersized potatoes produce small slices that fry faster and darken. Grading routes different sizes to different slicer lanes or to different product streams. The goal is to keep each slicer running within its preferred diameter range. Before slicing, potatoes are washed and often peeled depending on the crisp style. Spray washers remove soil and grit that would dull blades and darken oil. Peeling can be abrasive or steam-based. Abrasive peeling removes skin by rubbing against rough surfaces. Steam peeling loosens skin rapidly, which is then removed mechanically. Peeling choice affects yield and appearance. A peeled crisp tends to have a uniform, pale base color, while skin-on crisps show darker flecks and require tighter sorting later. Potato chemistry control is a major lever for color consistency. Reducing sugar levels in potatoes affect browning rate during frying. High reducing sugars lead to dark crisps at normal fry conditions. Plants manage this through raw material selection, blending of lots, and controlled storage temperature. Potatoes stored too cold can accumulate sugars and brown more. Potatoes stored too warm can sprout and lose solids. The plant aims for a consistent solids content and sugar level so the fryer can run at stable time and temperature. Once slices enter the fryer, the process becomes heat transfer and mass transfer. Moisture leaves the slice as steam. As water leaves, pores form. Oil replaces some of that volume as the slice cools and internal pressure drops. The factory manages oil uptake by controlling temperature, residence time, and slice thickness. Higher temperature drives faster moisture loss and can reduce total oil uptake, but it can also increase browning and fragility. Lower temperature increases residence time and oil uptake. The line balances these to hit a target oil content and color. Fryers are designed for uniformity. Oil is circulated and heated, so temperature is consistent across the belt width. Baffles guide flow to eliminate cold zones. Slice bed depth is controlled so slices are not stacked. Stacked slices insulate each other and cook unevenly. Many systems use in-feed spreaders that distribute slices into a single layer at fryer entry. Oil quality is maintained continuously. Filtration systems remove crumbs and starch fragments because they burn and darken the oil, creating off flavors and color specks. Oil turnover adds fresh oil and removes degraded oil fractions. Consistent oil quality gives consistent heat transfer and consistent browning. It also helps maintain a clean flavor profile. Color sorting is often used after frying. Optical systems detect overly dark crisps and eject them with air jets. Sorting helps manage natural raw material variation and keeps the bag consistent. It is especially useful when potatoes vary slightly in sugar content even after selection. The manufacturing process for Ruffles potato chips begins long before a potato even enters the production facility. It starts with agricultural planning and controlled sourcing. Ruffles, as a brand under Frito-Lay, utilizes proprietary potato varieties that are cultivated specifically for chip production. These aren't the same types of potatoes used for baking or mashing. Instead, Frito-Lay contracts with dozens of partner farms across the United States and other regions to grow chipping potatoes. Varieties like Atlantic, Snowden, or proprietary Frito-Lay hybrids that are selected for their specific characteristics: high dry matter content, low sugar levels, uniform shape, and dense texture. Each crop is grown with tight controls on irrigation, fertilizer use, and harvesting schedules to ensure consistency and minimize storage degradation. Potatoes that are too moist, sugary, or irregular in shape would result in chips that are oily, dark, or fragile, none of which meet the Ruffles brand standard. At harvest, potatoes are collected using automated harvesters equipped with rubber conveyors that minimize bruising. They're loaded into transport trucks and sent to the factory, often within a few days of being pulled from the ground. When the potatoes arrive at the processing plant, they enter the facility through the raw receiving bay. These are enclosed intake areas where truckloads are weighed, logged, and tested before being accepted for processing. At this point, technicians from the quality assurance team extract random samples from the load to check for size uniformity, sugar content, starch levels, and moisture content. Any batch of potatoes that falls outside the tight specification window may be rejected or diverted to other non-chip product lines. Once cleared, the potatoes are offloaded from the trucks into a large receiving pit, essentially a hopper connected to a series of conveyor belts. From here, the potatoes are moved toward the initial cleaning phase. This begins with the destoning drum. As the potatoes enter this large rotating cylinder, jets of water and the rotating action cause heavier materials, like rocks or clumps of soil, to separate and fall through grated bottoms. Potatoes are lighter and are lifted to the next stage. From the destoning drum, the potatoes enter the pre-wash flume system. A flume is a water-filled channel that moves product gently using the flow of water instead of belts. This minimizes physical damage to the raw potatoes while removing dirt and loose debris. The flume water is treated and recirculated through industrial filters and chemical dosing systems to ensure both sanitation and water conservation. In many modern plants, the water used in these systems is part of a closed-loop recovery system designed to reduce environmental impact. The next stop is the rotary scrubber. This is a long, cylindrical machine fitted with internal brushes that rotate as the potatoes pass through. High-pressure nozzles spray water as the tub rotates, scrubbing away any remaining mud, sand, or biological debris. The inside of the scrubber is lined with abrasive surfaces that help clean the rough skin of the potato without cutting into the flesh. The goal here is to deliver a clean, undamaged potato with its skin still intact, ready for inspection. After scrubbing, the potatoes are lifted out of the washer by a cleated incline conveyor and passed through a visual and automated inspection system. In this phase, both human inspectors and camera-based vision systems work in parallel. The conveyor belt is engineered to spread out potatoes into a single layer, and each tuber moves past a combination of high-resolution cameras and infrared sensors. These systems are trained to detect green spots, bruises, cuts, or signs of rot. Any substandard potatoes are rejected via automated diverter arms or air jets, which remove the faulty items from the belt and send them to waste or compost streams. Human operators stationed along the line also remove visibly defective items that machines might miss, such as those with odd shapes that won't slice well on the crinkle-cut blades. Every removed potato is scanned and logged into the factory's waste tracking system, allowing operators to identify trends and address upstream sourcing problems if too many rejects appear from a single truckload. Now that the potatoes have passed visual inspection, they move on to the peeling station. For Ruffles, peeling is essential. While some gourmet-style chips retain their skins, Ruffles chips require a smooth, peeled surface to produce clean, consistent ridges during slicing. Peeling is achieved using a combination of steam and abrasion in what's known as a steam peeler. The steam peeler is a high-pressure vessel that receives a batch of potatoes, seals the chamber, and subjects the potatoes to pressurized steam, usually around 180-220 psi for 8 to 20 seconds. This superheated environment rapidly loosens the outer skin layer by partially gelatinizing the pectin between the skin and the underlying tissue. Once the steam cycle ends, a sudden pressure drop causes the skin to puff and detach slightly from the flesh. Immediately after this, the potatoes are discharged into an abrasive roller peeler. This is a rotating drum lined with rough surfaces, often embedded with carborundum grit, that gently scrubs the now loosened skins away. Water sprays are used to flush away the skins and clean the exposed potato surface. The amount of skin removed is carefully monitored. Too much abrasion would remove usable flesh and increase waste. Too little would leave patches of skin that affect the slicing process. The peeled potatoes are rinsed again in chilled water to stop any residual thermal activity and prevent enzymatic browning. A small dose of food-safe antioxidant, like sodium metabisulfite or citric acid, may be added to the rinse water to preserve the pale color of the peeled surface and prevent discoloration before slicing. At this stage, the potatoes are fully clean, peeled, and ready for their signature transformation, being cut into the iconic ridged slices that define a Ruffles chip. With the freshly peeled and rinsed potatoes now ready for transformation, the next phase in the Ruffles production process focuses on slicing, the moment where whole tubers are precisely cut into their distinctive ridged form. The ridges are far more than a visual or marketing detail. They play a critical role in the chip's strength, texture, and frying performance. This stage involves advanced slicing technology, careful temperature and starch control, and continuous monitoring to ensure each slice is the exact thickness, shape, and structural consistency required for optimal cooking and crispness. The peeled potatoes are transported to the slicing area via gentle, water-based flumes or soft conveyor belts to minimize impact and prevent bruising. Once they reach the slicing units, the potatoes are fed one by one into high-speed rotary slicers designed specifically for crinkle or corrugated cuts. These industrial slicing machines use a rotating impeller or feed wheel to press each potato firmly against a stationary, razor-sharp cutting head fitted with ridged blades. The blades are precisely machined to form a consistent wave pattern, typically with a wave amplitude of 1.5, 2.5 mm and a thickness of around 1.3, 1.5 mm. Unlike flat chip slicing, where a smooth blade is sufficient, Ruffles require a carefully engineered ridged blade made of hardened stainless steel. These blades are aligned at specific angles to produce even, undistorted waves along the chip's entire surface. The sharpness, speed of rotation, and pressure exerted must be perfectly balanced. Too much force or misalignment can result in chips with uneven ridges or broken tips, which would either fry unevenly or be rejected later during inspection. The sliced potatoes are ejected from the slicing drum at high velocity and collected in a shallow trough or on a belt that immediately begins the next critical step: starch removal and surface moisture control. Every potato contains natural starch, and when sliced, a large amount of that starch is released onto the cut surfaces. If not removed, this surface starch can interfere with the frying process, causing chips to stick together, fry unevenly, or develop burnt spots. It can also result in a greasy or gummy mouthfeel, which is unacceptable for Ruffles' clean, crisp texture. To remove excess starch, the slices pass through a multi-stage rinsing system. In the first phase, they enter a flume filled with cold, recirculated water, where they are gently agitated to dislodge free starch. The water in this flume is constantly filtered and monitored for starch content, with automated control systems adjusting flow rate and replacement intervals to maintain effectiveness. Following the first rinse, the slices often move through a series of cascading rinse curtains, sheets of filtered water that fall like waterfalls over the slices as they travel along a mesh or perforated conveyor belt. This helps remove residual starch without applying any mechanical force that could break the delicate ridges. After rinsing, the slices must be dried to a specific degree, not fully desiccated, but dry enough on the surface to allow the hot oil in the fryer to crisp the exterior without creating steam pockets or excessive foaming. This is achieved using a dewatering shaker and an air drying tunnel. The dewatering shaker is a vibrating belt or tray that shakes the slices gently to remove bulk water. The slices then pass under high-velocity air knives, rows of precisely aligned jets that blast room temperature or slightly warmed air across the chip surface. The air knives are tuned to create a shearing effect that strips away surface moisture while maintaining the shape and integrity of the ridged cuts. At this point, the slices are considered ready for frying, but only if they meet one final set of pre-cook inspection criteria. Before entering the fryer, the slices pass through an optical sorting system. This state-of-the-art inspection station uses a combination of high-resolution cameras, infrared sensors, and sometimes laser scanners to detect defects such as green spots, bruising, overly large slices, or broken pieces. Defective slices are rejected with microbursts of compressed air, which knock them off the main conveyor line and into waste or reprocessing bins. The acceptable slices, meanwhile, are evenly distributed across the width of the fryer in feed conveyor to ensure uniform exposure to hot oil. Frying is where the raw slices become what we recognize as potato chips. And for Ruffles, this step is both art and engineering. The chips are fried in continuous fryers, long stainless steel troughs filled with high-temperature cooking oil. The oil is typically a carefully formulated blend of vegetable oils, often including sunflower, corn, or canola oil, chosen for their high smoke points, neutral flavor, and oxidative stability. The oil is filtered, treated, and replaced on a tightly regulated schedule to maintain quality and avoid flavor degradation. As the slices enter the fryer, they are immediately submerged by a submersion conveyor that ensures they stay evenly beneath the oil's surface throughout the cooking process. The oil is maintained at a precise temperature, usually between 170 degrees Celsius and 190 degrees Celsius. This range is critical. Too cool, and the chips absorb oil and turn soggy. Too hot, and they brown too quickly or develop burnt notes. Each chip is cooked for approximately 2 to 3 minutes, depending on thickness, oil composition, and desired moisture content. Inside the fryer, the chips expand slightly and crisp as their internal water content rapidly evaporates. The ridged surface of Ruffles causes the chip to fry unevenly by design, creating micro variations in texture that result in a more substantial bite and greater structural integrity. The ridges also slow oil drainage, allowing a slightly longer dwell time that contributes to the chip's durability and resistance to breakage during dipping. The fryer is equipped with multiple sensors and flow meters that measure oil temperature, turnover rate, chip feed rate, and even in-oil moisture concentration. These data are analyzed in real time by the factory's central control system, allowing operators to make immediate adjustments. In many facilities, the frying process is linked to upstream slicing sensors. For example, if slightly thicker slices are detected coming from the cutter, the fryer conveyor speed is slowed accordingly to ensure proper cook time. As the chips emerge from the fryer, they pass through an oil draining phase. A vibrating conveyor with a perforated surface allows excess oil to drip off. This is immediately followed by an air cooling system that begins to lower the chip's temperature, halting further cooking and locking in texture. Cooling is essential not only for texture stability, but also to prepare the chips for seasoning, which happens shortly after. But before we get to seasoning, there's a critical interlude in the process: moisture analysis and inline quality control. At this stage, a small percentage of chips are diverted through a sampling chute to a nearby test station. Here, technicians use moisture analyzers, color meters, and even acoustic crispness testers to evaluate product characteristics. These tests ensure that the chips meet the factory's targets for final moisture content, color uniformity, and physical integrity. As the freshly fried and cooled Ruffles chips exit the fryer and pass through preliminary quality control, they enter one of the most dynamic and highly controlled stages in the factory: seasoning. This is the phase where the chips receive their final flavor identity, whether it's the original lightly salted variant, sour cream and onion, cheddar and sour cream, jalapeno ranch, or any of the other regional and seasonal flavor options Ruffles is known for. Applying these flavors evenly, consistently, and at high speed while preserving the chip's structural integrity and minimizing waste is a challenge that modern factories solve using specialized equipment and real-time process monitoring. The chips arrive at the seasoning station on a wide, inclined conveyor or vibratory tray that serves two main functions. It spreads the chips out into a single layer to prevent overlap, and it gently agglomerates chips to control their flow into the seasoning drum without damaging them. Due to the ridged shape and the thicker cut of ruffles compared to standard potato chips, seasoning application must account for deeper surface area and variable orientation. Some chips will face ridge side up, some down, some angled. Seasoning application takes place inside a rotating tumbler drum, also called a flavor drum or seasoning cylinder. This stainless steel drum is set at a slight incline and constantly turns on its horizontal axis, gently lifting and tumbling the chips while they rotate through it. At the entrance to this drum, a continuous metered flow of seasoning powder is dispensed through an auger-based dosing system. The seasoning blend, pre-mixed according to a proprietary formula, includes a combination of salt, natural and artificial flavorings, cheese powders, dehydrated dairy, onion and garlic powders, spices, yeast extract, and anti-caking agents. The dosage rate of the seasoning is tightly controlled via real-time feedback systems. Optical sensors measure the chip volume entering the drum, and the dosing screw adjusts the delivery rate to maintain an ideal flavor to surface area ratio. Too much seasoning leads to clumping, over-salted chips, and waste. Too little results in bland or unevenly flavored chips that fail quality checks. For cheese-based seasonings, which are more moisture sensitive, the flow system may include a nitrogen-purged hopper or desiccant units to prevent clumping in humid environments. Inside the flavor drum, fine misting nozzles also spray a light coating of oil to help the seasoning adhere evenly to the chip surface. This atomized oil does not soak the chips, but rather creates a microfilm that holds the powder in place without compromising crunch. The rate of oil application, angle of spray, and temperature are all adjusted based on the type of seasoning used. For example, heavily coated varieties like cheddar and sour cream require more binder oil and a slightly longer tumbling duration to ensure every chip is fully and evenly coated. Throughout the seasoning process, line operators and quality assurance technicians take random samples every few minutes. These samples are assessed for seasoning coverage, color intensity, and surface powder levels. In more advanced factories, seasoning uniformity is checked with hyperspectral cameras that scan the chips as they exit the drum, detecting variations invisible to the human eye and triggering alerts or auto-calibration if inconsistencies are detected. Once the chips have been properly seasoned, they are transferred to the packaging phase. This is a highly automated and synchronized system that must meet several objectives simultaneously. Protect the chips from breakage, preserve freshness, prevent contamination, provide product information to the consumer, and maintain traceability for safety audits. Packaging begins with product accumulation. Conveyors from multiple seasoning drums may feed into a single accumulation hopper or weigher, depending on line configuration. This hopper temporarily holds chips before they're dispensed into individual bags via a multi-head combination weigher. A multi-head weigher is an advanced piece of equipment with multiple radial feed hoppers arranged in a circular pattern. Each hopper releases a small portion of chips, and a central computer instantly calculates which combination of hoppers adds up closest to the target weight, say 28.3 grams for a single serve bag. This combination is released simultaneously into a timing hopper, which drops the exact weight into a vertical form-fill-seal packaging machine. The VFFS machine forms bags from a continuous roll of printed plastic film, often made from multi-layer laminate materials with barriers against oxygen, light, and moisture. As the chips drop from the weigher into the forming tube, the film is pulled around the tube, sealed lengthwise, and sealed again at the top and bottom with heated jaws, creating a pillow-style bag. Before the top seal is made, a precise dose of nitrogen gas is injected into the bag, a process known as nitrogen flushing. This replaces the oxygen-rich air inside the package to reduce oxidation, extend shelf life, and protect the chips from crushing by slightly inflating the bag. Once sealed, Each bag moves through a print station where batch codes, production time, plant ID, and expiration dates are applied using inkjet or thermal printers. Bags then pass through check weighers to confirm accuracy. Any bag outside the designated weight window is automatically rejected and diverted to a rework bin. Metal detectors or X-ray systems scan every bag to ensure no foreign objects have entered the product during processing. This is standard for all snack food production and a critical part of food safety compliance. From there, the sealed and verified bags are grouped into cartons or display trays by robotic case packers. These cartons are sealed with tape or glue and labeled with barcodes and tracking information. Finally, cartons are stacked onto pallets by robotic palletizers, often using suction cup grippers or clamp arms to gently stack without damaging contents. Pallets are wrapped in stretch film and staged in the finished goods warehouse, which is climate controlled to preserve chip texture and flavor. At every point along this packaging line, sensors, programmable logic controllers, and SCADA systems monitor performance metrics, line speed, reject rates, weigher accuracy, sealing temperature, film feed rate, and more. Maintenance logs and process trends are analyzed weekly to identify emerging issues, improve throughput, and reduce product loss. Beyond the physical movement of chips, there are strict sanitation and allergen management systems in place. Since some Ruffles flavors may contain milk, cheese, or other allergens, production lines must be deep cleaned between flavor runs. Clean in place protocols involve dismantling sections of the line using high-pressure washdowns, food-safe detergents, and microbial swab testing. Detailed records of every cleaning cycle are logged and audited regularly. In addition to cleaning, factories must manage cross-contamination risk during flavor changeovers. This includes running purge batches, segregating flavoring agents in separate storage silos, and using dedicated feed lines wherever possible. Every batch of Ruffles is linked back to a full traceability profile, covering raw material lot codes, equipment used, line operator IDs, and environmental conditions during processing. As the freshly packaged Ruffles chips leave the main production floor, the final phase of manufacturing comes into focus. A sophisticated web of logistics, sustainability efforts, continuous process optimization, and digital innovation. While the chips themselves are complete, the factory does not pause. Instead, a parallel system of data analysis, quality assurance, and supply chain orchestration continues operating in the background, ensuring the product not only meets current demand, but evolves to meet future expectations. These behind-the-scenes processes are integral to the long-term efficiency, environmental responsibility, and market success of Ruffles. At the heart of these operations is a factory-wide data infrastructure that tracks every input and output, from raw potatoes to finished pallets. Each batch of Ruffles produced is logged into an integrated manufacturing execution system. This software records the origin of each ingredient, the time and conditions of each processing step, the performance of every machine along the line, and even environmental metrics like room humidity and oil turnover frequency. The MES integrates with enterprise resource planning systems, providing real-time visibility into inventory levels, sales forecasts, and raw material consumption. This data is not merely archived, it's analyzed continuously using advanced analytics platforms and AI-based algorithms. These systems look for patterns in machine downtime, chip reject rates, oil consumption per batch, or seasonal fluctuations in potato solids. If a fryer begins to show a subtle increase in oil absorption, or if seasoning coverage becomes slightly more variable, the system flags it. Maintenance crews and process engineers receive alerts and can intervene before the issue affects product quality or efficiency. Predictive maintenance models also help avoid equipment failure by identifying when motors, pumps, or slicers are approaching wear thresholds. One of the key areas of focus in modern Ruffles factories is oil management. Frying oil is both a major cost and a major variable in product consistency and sustainability. The oil in the continuous fryer is constantly recirculated through filtration units that remove chip fines and particulates. Inline sensors monitor the free fatty acid content, color, and total polar materials in the oil, 3 indicators of oil degradation. When these metrics exceed defined limits, the system initiates partial or full oil replacement protocols. Some facilities have implemented smart fryer systems that dynamically adjust oil flow and heat profiles based on chip load and moisture level, significantly reducing oil turnover without compromising flavor or texture. Environmental sustainability is another priority embedded into Ruffles manufacturing. Frito-Lay, the parent brand, has committed to reducing water, energy, and greenhouse gas emissions across its snack food plants. One way this is achieved is through water reclamation. The flume water used to transport, wash, and rinse potatoes is filtered, UV treated, and reused multiple times before final disposal. Similarly, the steam peelers are equipped with condensate recovery systems that recycle steam condensate back into the boiler system, conserving energy and reducing water use. Electricity usage is optimized through variable frequency drives on conveyors and pumps, while LED lighting, motion sensors, and insulated cooling tunnels help minimize unnecessary energy waste. Some Ruffles production plants are now partially powered by renewable sources, including solar panels and biogas captured from on-site food waste digesters. Waste heat from fryers is recovered using heat exchangers and used to preheat incoming wash water, further boosting energy efficiency. Waste management is another crucial part of the factory's operations. Trimmings from biscuit cuts, chips rejected for size or overcooking, and seasoning overage are all collected, logged, and sent to animal feed processors or converted into biofuel when food safety protocols allow. Even the excess oil removed during de-oiling phases is collected, filtered, and sold to biodiesel manufacturers. Packaging materials are optimized for minimal plastic use, and packaging engineers continuously evaluate new laminates that offer better barrier performance with reduced environmental impact. Few snacks on the market capture the attention of consumers quite like Takis. With their signature rolled shape, vibrant colors, and explosive spicy flavors, Takis have carved out a unique space in the world of extruded corn snacks. Originally created by Barcel, a Mexican subsidiary of the Bimbo Group, Takis have grown from a regional novelty to a global snacking sensation. But behind each intensely flavored bite is a fascinating and highly engineered manufacturing process that brings together agricultural science, mechanical precision, and food chemistry on a massive industrial scale. To understand how Takis are made in a factory, we must begin at the very first stage, the sourcing of raw materials. The cornerstone ingredient in Takis is corn, more specifically, degermed corn flour, often referred to as mesa flour. This flour is derived from yellow or white field corn, grown primarily in the United States and Mexico. The corn used must meet specific quality parameters, particularly in terms of kernel size, moisture content, and starch composition. Contracted farmers typically grow this corn under strict agronomic practices to ensure high yield and consistent quality. Once harvested, the corn is transported to centralized milling facilities, where it undergoes a critical transformation. This transformation begins with the nixtamalization process, a traditional method that dates back to ancient Mesoamerican civilizations. In modern milling operations, dried corn kernels are steeped in a lime water solution, water mixed with food-grade calcium hydroxide at controlled temperatures for several hours. This chemical soaking loosens the hulls, softens the kernels, and alters the protein and carbohydrate structures, improving both flavor and digestibility. Once steeped, the corn is thoroughly washed to remove residual lime and loosen pericarp. What remains is nixtamalized corn, which is then ground through industrial stone mills or hammer mills into a fine, homogeneous masa dough. For Takis, however, the masa is taken one step further. Instead of being used wet, as in tortilla production, it is dried and ground again into a shelf-stable masa flour. This dried masa, now fine and moisture-free, serves as the primary input in the Takis production process. It's stored in massive silos within the factory, equipped with aeration systems to keep the flour dry and flowing freely. Pneumatic conveyors transfer the flour to precise metering hoppers above the mixing equipment. Here is where the transformation from flour to snack begins in earnest. The masa flour is dropped into high-capacity industrial mixers, where it is blended with water and a proprietary mixture of seasonings, emulsifiers, and sometimes oil. These mixers are equipped with temperature control systems and paddles designed to evenly distribute moisture throughout the blend. The goal is to create a pliable yet firm dough that is suitable for extrusion, a process that will ultimately define the iconic Takis shape. The mixed dough is conveyed directly to the extruder, a high-pressure, high-temperature piece of equipment that lies at the heart of many snack food manufacturing lines. For Takis, a twin-screw extruder is typically used. The dough is fed into the extruder barrel, where rotating screws push the material forward while simultaneously mixing, shearing, and heating it. Inside the barrel, steam pressure rises dramatically due to intense friction and controlled moisture. This heat gelatinizes the starches within the masa, turning the dough into a malleable, semi-cooked matrix. At the end of the extruder barrel lies a die plate with specially engineered openings. These dies are shaped to produce flat ribbons of masa with uniform width and thickness. As the dough exits the extruder, it experiences a sudden drop in pressure, causing it to puff slightly, though not excessively, as takis are denser and more compact than puffy snacks like cheese curls. Automated blades then cut the ribbons to a standardized length, usually between 4 and 6 inches. Now comes one of the most recognizable steps in the process, the rolling. Using a synchronized series of mechanical arms and belt-driven rollers, each flat strip is quickly rolled into a tight cylinder, mimicking the appearance of a small, rolled taco or taquito. This is done at high speed, often in under a second per piece, with careful calibration to prevent unrolling or uneven shapes. The rolling units must operate with precise timing and alignment, as even small inconsistencies could result in defective product or downstream clogging. Once formed, the raw Takis are transferred onto a mesh conveyor belt that carries them into the continuous fryer. Unlike air-puffed snacks, Takis achieve their final texture and flavor through frying in hot oil. The frying process occurs in large stainless steel fryers filled with high-stability vegetable oil, typically corn or sunflower oil. The oil is maintained at a consistent temperature, usually around 350 degrees Fahrenheit, and is constantly filtered and replenished to maintain quality and prevent flavor degradation. As the Takis pass through the fryer on a conveyor, they cook rapidly, the exterior crisping while moisture evaporates from the interior. This gives Takis their signature crunch, dense and satisfying, with just enough resistance to offer a unique mouthfeel. The fry time is carefully controlled, usually around 30 to 60 seconds, to ensure even cooking without burning or excessive oil absorption. Temperature sensors, oil flow meters, and automated timing systems monitor every batch, with defective products automatically rejected by vision systems downstream. As soon as they exit the fryer, the Takis must be cooled rapidly to halt cooking and prepare them for seasoning. The hot snacks are dropped onto a vibrating cooling conveyor, which uses forced, ambient, or chilled air to bring their temperature down quickly. This conveyor system not only cools, but also aligns and spreads the product evenly, preventing clumping before seasoning. And this is where the flavor magic happens. Takis are famous for their bold and intense seasoning blends, most notably the Fuego variety, which combines hot chili pepper and lime. The cooled snacks enter a large rotating tumbler or flavor drum, where they are coated with a fine mist of oil or flavor adhesive, such as maltodextrin or gum arabic. This light coating ensures the powdered seasoning sticks uniformly to the surface. Then, a precisely metered amount of dry seasoning blend is sprayed onto the rolling Takis within the drum. The tumbler rotates at a controlled speed, ensuring that every piece receives an even coating of the intensely red, flavor-packed powder. The powder itself is a carefully engineered blend of spices, acids, artificial flavors, and colorants, many of which are micro-encapsulated to preserve potency until consumption. This step is where flavor engineers shine, crafting bold profiles that hit the palate in waves. First, the citrusy tang of lime, then the slow-building burn of capsaicin from chili powder, followed by savory umami notes and salt. Once the Takis are evenly coated with their signature seasoning, the product advances to the post-seasoning inspection stage. Here, quality control takes center stage. As the finished snacks move down the conveyor belt, they pass through a combination of optical sorters, weight sensors, and human oversight stations. These systems are tasked with identifying any irregularities, broken pieces, improperly seasoned rolls, or foreign particles. High-speed cameras analyze each item against a programmed standard, with air jets used to automatically divert defective snacks from the production line. This meticulous approach ensures uniformity in every batch, both in appearance and taste. After clearing inspection, the freshly seasoned Takis enter the final phase of the production process: packaging. In large-scale manufacturing operations, packaging is not merely about enclosing the product in a bag. It's a tightly orchestrated, high-speed operation designed to maintain freshness, ensure food safety, and optimize shelf life. The cooled Takis are funneled into hoppers that portion them into individual servings. These hoppers are mounted above form-fill-seal machines, or FFS machines, which are the heart of the packaging operation. Each FFS unit starts with a continuous roll of multi-layered packaging film. This film is typically made from a combination of materials such as polyethylene, aluminum, and polypropylene. These layers provide essential barrier properties, keeping out oxygen, light, and moisture, elements that would otherwise degrade the snack's flavor and texture. The film roll is unwound, shaped into a tube, and sealed along its vertical edge using heat-sealing bars. Simultaneously, the bottom of the tube is sealed to form a pouch, into which a precise dose of Takis is dropped from the hopper above. As the filled pouch moves through the machine, a horizontal seal is applied at the top, closing the package and completing the bag. The result is a perfectly sealed, shelf-ready snack pouch. Some facilities also inject an inert gas, typically nitrogen, into each bag before sealing. This process, called nitrogen flushing, displaces oxygen and helps prevent oxidation of the oil and spices inside the snack. It's a key technique in preserving freshness for weeks or even months after production. But the packaging line doesn't stop there. Once sealed, the Takis bags are conveyed to the labeling and coding station. Here, high-speed inkjet printers apply critical data to each bag, including production date, batch code, and expiration date. These codes are essential for traceability, enabling both the manufacturer and regulatory bodies to track products through the supply chain and, if necessary, initiate a recall. In larger factories, barcode scanners validate each print in real time, flagging any unreadable or incomplete prints for immediate rework. Next, the finished snack bags are grouped into larger quantities for secondary packaging. Robotic arms equipped with suction grippers or mechanical claws pick up batches of bags and place them into cardboard cartons or shrink-wrapped bundles. These secondary units are ideal for distribution to retailers, vending machine suppliers, and food service channels. Automated case erectors, packers, and palletizers handle this stage with minimal human intervention, ensuring consistency and speed. Once boxed, the cartons are scanned one final time, then transported to the warehouse using automated guided vehicles or conveyor systems. The warehouse itself is climate controlled, maintaining ideal conditions for snack storage, typically around 70 degrees Fahrenheit and low humidity. Inventory management systems track every pallet, integrating with enterprise resource planning software to coordinate distribution across multiple regions and customer channels. At this stage, Takis are officially ready for distribution. Depending on the destination, pallets may be routed to regional distribution centers, export facilities, or directly to major retailers. In the US, this typically involves refrigerated trucks or dry vans with temperature and humidity monitoring systems to ensure the product remains in peak condition throughout transport. For international shipments, Takis are loaded into containers and shipped via freight lines, with each load accompanied by customs documentation, certificates of analysis, and food safety verification records. It's important to note that all these stages, milling, extrusion, frying, seasoning, packaging, and shipping, operate under strict regulatory compliance and food safety protocols. The Takis manufacturing facility is typically audited regularly by health authorities and third-party certification bodies to maintain good manufacturing practices and adherence to standards such as the Global Food Safety Initiative, HACCP, or hazard analysis, and critical control points is implemented throughout the line to identify and mitigate risks, from biological contamination to mechanical hazards like metal fragments. Metal detectors and X-ray machines are also integrated into the production line post-frying and pre-packaging. These systems serve as a critical control point, scanning every product to detect foreign objects that could compromise consumer safety. In the rare event a contaminant is found, the system immediately shuts down the line and activates traceability protocols, ensuring the source of the contamination is quickly identified and corrected. In addition to food safety, automation plays a crucial role in the consistency and scalability of Takis production. Modern factories are outfitted with CAD systems, supervisory control, and data acquisition, which allow operators to monitor and adjust every part of the process in real time. Temperature readings, fry times, dough consistency, seasoning distribution, packaging integrity, all of it is visible from centralized control rooms staffed by trained technicians. These systems also gather historical data, enabling predictive maintenance and process optimization over time. Moreover, the human element remains vital. Quality assurance personnel regularly conduct sensory evaluations to ensure the finished product matches the flavor, aroma, and texture profile that consumers expect. Samples are pulled at set intervals and subjected to detailed analysis, including moisture content testing, oil content analysis, pH measurements, and microbial testing. These assessments help maintain product consistency and detect any early signs of spoilage or variation. And let's not forget the environmental impact. Many modern snack food factories, including those producing Takis, are actively investing in sustainable practices. Waste heat from fryers is often reclaimed and used to preheat water or air elsewhere in the facility. Oil used in frying is filtered and recycled several times before final disposal. Packaging materials are increasingly being sourced from recyclable or biodegradable films, and energy-efficient motors and lighting systems reduce overall factory emissions. The success of Takis also hinges on innovation. Flavor development is a continuous process involving food scientists, sensory analysts, and marketing teams. New flavors are often trialed in small-scale batch lines within pilot plants, where formulation tweaks can be made rapidly without disrupting full-scale production. Once a new variety passes consumer testing, it's scaled up to the main line, where production parameters are adjusted to accommodate the unique characteristics of the new seasoning blend. In essence, every bag of Takis represents a fusion of ancient techniques and cutting-edge food science. From the Mesoamerican tradition of nixtamalized corn to the robotic arms and AI-controlled inspection systems of a 21st century factory, the journey from cornfield to snack aisle is a marvel of industrial engineering. The attention to detail, the layers of safety checks, the complex choreography of machines, and human oversight all come together to create that iconic crunch and fiery kick that snack lovers around the world have come to crave. Once the freshly sealed Takis packages leave the manufacturing floor, their journey is far from over. The next phase, post-factory logistics and storage, is just as critical to the integrity of the final product. From the moment those pallets are loaded onto the loading docks, every step must be meticulously orchestrated to maintain freshness, comply with regulatory requirements, and meet retailer timelines. Palletized shipments of Takis are typically staged in designated outbound logistics zones within the factory's warehouse. Here, inventory management systems, integrated with warehouse management software, guide automated forklifts or human operators in sequencing outgoing loads. Each pallet is tagged with RFID or scannable barcodes, providing traceable data like batch number, production date, customer destination, and handling instructions. This is especially vital in high-volume operations where hundreds of thousands of units move through daily. Distribution of Takis often begins with transfer to regional distribution centers, or RDCs. These massive hubs serve as strategic points between the manufacturing facility and the retail shelf. Transportation is conducted via trucks equipped with climate control systems to protect the product from temperature spikes or humidity, both of which could compromise the texture and flavor of the highly seasoned snack. Although Takis are non-perishable, they are still sensitive to environmental conditions due to the oil content and delicate nature of their fried, rolled structure. Upon arrival at RDCs, the pallets are unloaded and sorted according to their final destination. Some may be earmarked for export, requiring additional customs documentation and compliance with international food labeling standards. For domestic markets, the focus shifts to inventory allocation, wherein Takis are divided among retailers based on demand forecasts, sales trends, and marketing campaigns. Algorithms calculate optimal shipping routes and timelines to minimize storage time and maximize shelf life for consumers. In-store delivery typically occurs on a just-in-time basis. Retailers prefer to receive snack shipments shortly before they are needed for shelf restocking to reduce their own warehousing costs. Specialized delivery trucks make daily or weekly runs to supermarkets, convenience stores, gas stations, and even vending machine distributors. Each of these retail environments poses unique packaging and merchandising challenges, all of which were anticipated back at the design and branding stage of the Takis production cycle. One of the unsung heroes in the journey of Takis is the shelf life optimization strategy. Although the product is fried, which naturally reduces moisture content and microbial activity, the seasoning powders and oils are susceptible to degradation over time. To combat this, manufacturers employ a suite of preservation techniques. Nitrogen flushing, as mentioned earlier, displaces oxygen in the sealed package, but antioxidants like tocopherols or rosemary extract are often blended into the seasoning to prevent rancidity. Additionally, desiccant sachets are sometimes included in bulk packaging layers to absorb ambient moisture during long-haul shipping. Once Takis make it to the retail environment, product rotation and visual appeal become the next critical concerns. Merchandising teams work with stores to position Takis in eye-catching locations, often near checkout counters or in custom display racks. Packaging design plays a crucial role here. The vivid purple of the Fuego flavor, for instance, has become iconic. This is not accidental. It is the result of extensive consumer psychology research and competitive shelf analysis. The packaging is printed using high-intensity inks and UV-cured varnishes that resist fading under fluorescent retail lighting. Meanwhile, behind the scenes, the manufacturer continues to monitor product performance through various feedback loops. Point-of-sale data is constantly reviewed to identify hot-selling regions, seasonal trends, and underperforming SKUs. Social media sentiment analysis and direct consumer feedback also guide adjustments in flavor intensity, packaging size, and promotional strategies. All of this feeds back into the product lifecycle management software, which helps guide future production and flavor development decisions. Speaking of flavors, one of the most fascinating aspects of the Takis operation is the flavor innovation pipeline. Flavor development is not merely a matter of combining spices, it's a complex interplay of sensory science, market forecasting, and precision engineering. Within dedicated R&D facilities, flavor scientists and food technologists explore new seasoning blends that push boundaries while remaining accessible to a wide audience. Using a combination of gas chromatography, mass spectrometry, and trained sensory panels, they deconstruct flavor experiences into measurable data points. For example, developing a new flavor like Dragon Sweet Chili or Blue Heat begins with identifying flavor trends in regional and global markets. Are consumers leaning toward Asian-inspired profiles? Are younger audiences seeking spicier, more adventurous options? Once a flavor theme is chosen, food scientists begin formulating dry seasoning blends that meet those goals. These blends are then micro-encapsulated to maintain potency through the frying process, ensuring that the end product retains its flavor intensity after months on the shelf. Prototypes are created on small-scale extrusion and seasoning lines within pilot plants. Here, the entire Takis production process is simulated at a reduced scale. This allows for rapid testing of texture, color retention, seasoning adhesion, and oil interaction without interrupting full-scale operations. Multiple iterations may be required before the formula is finalized. Once approved, the new flavor is scaled up and introduced into the market through limited releases or promotional campaigns. Based on consumer reception, it may join the permanent lineup or serve as a limited time offering. But with every new flavor comes new challenges. Seasoning powders vary in density, oil absorption, and electrostatic properties, all of which affect how they adhere to the snack. The tumbler rotation speed, spray nozzle angle, and even drum temperature may need to be recalibrated to accommodate different blends. For spicy varieties, capsaicin levels must be carefully controlled not only for flavor balance, but also to comply with regional regulatory thresholds for spice labeling. Some jurisdictions require heat warnings if the Scoville rating exceeds a certain level. Furthermore, regulatory compliance is a continuous effort in every phase of production. Labels must accurately reflect ingredients, nutritional values, and allergens. In countries like the US, compliance with FDA labeling laws is mandatory. In the European Union, Takis must also adhere to FSA food additive regulations and translation requirements. This means each regional variant may have slightly different formulations or packaging to meet local standards. Another area of innovation is sustainability. Snack food factories around the world are under increasing pressure to reduce their environmental footprint. The Takis production chain is no exception. Some facilities have introduced biodegradable packaging options for select markets, while others have invested in solar panels and high-efficiency fryers to cut energy use. Spent cooking oil is now commonly collected and converted into biodiesel, and water used in nixtamalization is filtered and reused for non-contact applications like equipment cooling. Sustainability also intersects with supply chain ethics. Corn suppliers are vetted not only for quality and price, but also for compliance with labor and environmental standards. Supplier audits are conducted regularly, and digital traceability platforms are used to map the corn's journey from field to fryer. This level of visibility allows the manufacturer to ensure that every ingredient in a Takis snack aligns with their corporate responsibility goals. Takis, for all their fiery boldness and snackable appeal, are a masterclass in food engineering and global logistics. They represent what happens when cultural flavors are married with advanced manufacturing, when age-old ingredients are given new life through extrusion science, and when every detail, from the grind of the corn to the curve of the roll, is tuned for maximum consumer satisfaction. As the Takis brand continues to evolve, the role of emerging technology in snack production becomes increasingly pronounced. Digital twins, for instance, are now being introduced in advanced food manufacturing environments. These are real-time digital replicas of the physical production line, complete with sensors, predictive analytics, and machine learning algorithms. By modeling the entire extrusion and frying process digitally, operators can simulate how small changes in variables, such as dough moisture content, oil temperature, or seasoning particle size, will impact the final product before making physical adjustments. This minimizes downtime, reduces waste, and enhances consistency across batches. Artificial intelligence and machine vision systems are also revolutionizing quality control. High-resolution cameras paired with deep learning algorithms can now detect subtle flaws that human inspectors might miss, such as uneven seasoning, microfractures in the rolled snack, or variations in color that could indicate improper frying. These systems learn over time, refining their detection capabilities with each batch they analyze. This not only improves product quality, but also enhances traceability and accountability within the plant. One particularly forward-looking development is in the realm of alternative ingredient sourcing. As demand for gluten-free, vegan, and allergen-free snacks continues to rise, food scientists are exploring reformulations of Takis that use alternative flours, such as chickpea, lentil, or sorghum flour. These flours come with their own extrusion challenges, especially when it comes to texture and structural integrity. Specialized extruder screws and preconditioning treatments may be necessary to match the crispness and density of the original corn-based recipe. Flavor delivery is another frontier being actively developed. Microencapsulation technologies are growing more sophisticated, allowing for flavors to be released sequentially as the snack is chewed. This creates a dynamic sensory experience, perhaps a burst of lime, followed by a wave of chili heat, then a subtle, lingering smokiness. These multi-layered flavor profiles are tested rigorously in consumer panels and sensory booths, with metrics like aftertaste duration, palate burn intensity, and residual coating all logged and analyzed. All these innovations are feeding into a broader trend: personalization. The concept of mass-customized snacks, where consumers can choose their preferred heat level, flavor intensity, or seasoning combo, may soon become viable thanks to modular production lines and just-in-time mixing systems. Imagine entering a vending machine interface or online store where you could build your own Takis variant, which is then mixed and packed to order within minutes. Is whole grain yellow corn, chosen for its high starch content, consistent kernel size, and clean flavor profile. The corn is sourced from farms that meet strict quality standards, often grown in regions where soil conditions, temperature, and moisture levels yield the optimal crop. The grain suppliers must pass multiple certification checks to ensure there are no contaminants, pesticides above allowed thresholds, or off-spec kernels. Alongside the corn, other ingredients such as sugar, malt flavoring, and a precise blend of vitamins and minerals are procured from certified ingredient suppliers. Even minor ingredients undergo laboratory testing for purity and safety before they are ever allowed into the production flow. When the corn arrives at the Kellogg's plant, it is unloaded from bulk transport trucks or rail cars into massive silos. These silos are fitted with aeration systems to keep the grain dry and prevent mold growth. Before storage, the corn passes through a preliminary cleaning system. This includes vibrating screens to remove large debris, aspirators that blow away dust and light particles, and magnetic separators to capture any stray metallic fragments. The cleaned corn is then weighed using automated bulk scales, ensuring precise tracking of raw material usage for both production planning and regulatory compliance. From storage, the corn moves toward the first processing step, cooking. But before cooking, the kernels need conditioning. This involves sending them through a pre-wet process in which they are steamed lightly or soaked in warm water to raise their internal moisture content to the right level for even cooking. Moisture meters along the line continuously monitor this process. Once conditioned, the kernels are conveyed to large pressure cookers, sometimes referred to as steam cookers or rotary pressure vessels. These massive stainless steel cylinders rotate slowly while injecting steam and adding a carefully measured solution of sugar, malt flavor, and salt. The steam not only cooks the kernels, but also helps the added flavors penetrate evenly into each piece of corn. The cooking process gelatinizes the starch inside the kernels, making them ready for the next transformation. After cooking, the hot, softened kernels need to be cooled and partially dried. They exit the cooker onto a series of vibrating cooling conveyors where ambient or slightly chilled air is blown across them. This stops the cooking process, stabilizes the texture, and prepares them for the critical flaking stage. However, the corn is still too moist to be flaked properly. It first enters large industrial dryers, often drum style or fluidized bed dryers, which reduce the moisture content to an exact level that will allow the flakes to shatter cleanly, rather than smear or tear during rolling. The drying process is closely monitored by moisture probes and computer-controlled exhaust systems to maintain uniformity. The next stop is tempering. Tempering involves holding the cooked, dried kernels in large bins for several hours so the remaining moisture distributes evenly throughout each kernel. This equalization is key to creating flakes that cook evenly in the final toasting step. The bins are equipped with gentle agitators or slow conveyors to prevent clumping and to keep airflow steady. Once tempered, the kernels are ready for the flaking process. Here, they pass through massive flaking mills. Each mill consists of two large, precision-ground steel rollers, often cooled internally to prevent heat buildup. These rollers press each kernel flat in a single pass, creating the familiar, thin, oval shape. The gap between rollers is set to a fraction of a millimeter and is adjusted automatically to ensure all flakes have the same thickness. The flaking mill is one of the most critical pieces of equipment because the thickness of the flake determines not only the texture, but also the way it will toast and absorb milk later on. Freshly flaked corn is still pale and slightly soft, so it moves immediately into the toasting ovens. These ovens are long, multi-zone conveyors where hot air, often at temperatures over 300 degrees Fahrenheit, flows over and through the flakes. The first zones drive off remaining moisture, while the later zones caramelize the sugars and develop the golden brown color. The toasting stage is where the signature crunch develops as the starch matrix hardens. The aroma at this point is unmistakable. Warm, slightly sweet, and distinctly cereal-like. Automated sensors monitor the color and moisture level, and adjustments to air temperature or conveyor speed can be made in real time to maintain consistency. Once toasted, the flakes are cooled on open conveyor belts with filtered ambient air. Rapid cooling helps lock in crispness and prevents condensation inside the packaging later. At this stage, the cereal may pass under a vitamin and mineral application system. In some Kellogg's cereals, a fine mist or powder of fortified nutrients is sprayed or dusted onto the flakes, then gently tumbled to ensure uniform coating. The application rate is measured to fractions of a gram to comply with nutritional labeling requirements. From here, the flakes head toward the packaging. Before they can be boxed, the cereal is screened to remove overly small particles or broken flakes. These screenings may be collected for use in other products or as livestock feed. The main product stream passes through a final quality check, which can include metal detectors, optical sorters, and even X-ray scanners to detect any foreign matter. Samples are pulled at regular intervals and sent to an on-site lab, where technicians test for moisture content, color, flavor, and texture to ensure the batch meets Kellogg's specifications. The packaging line is a marvel of precision. The cooled cereal is metered into form-fill seal machines or pre-made bag fillers. In the classic box format, an inner bag made of food-grade plastic film is formed from a continuous roll, filled with an exact weight of cereal using high-speed scales, then heat-sealed. The filled bag is automatically inserted into a printed cardboard carton, which is glued shut and stamped with a production code for traceability. Packaging machines operate in perfect synchronization with the upstream production flow to prevent overfill, underfill, or product jams. Sealed boxes travel down conveyors to be bundled into shipping cases. Robotic case packers arrange multiple boxes into corrugated cardboard cases, which are sealed and labeled with both barcodes and batch codes. These cases are stacked by robotic palletizers into tall, stable loads, often wrapped with stretch film to secure them for transport. From the moment the corn arrived at the plant, the environment has been strictly controlled for food safety. Air is filtered, surfaces are sanitized regularly, and all equipment is cleaned in place using automated cleaning systems that circulate hot water and food-safe detergents through the machinery. Employees follow stringent hygiene protocols, including wearing protective clothing, hairnets, and gloves. Every step in the process is documented for traceability, so that in the rare event of an issue, the source can be identified and contained quickly. Once the pallets of finished cereal leave the plant, they are loaded into clean, dry trucks or shipping containers. Distribution centers receive the pallets, store them under controlled conditions to prevent moisture pickup or crushing, and coordinate shipments to retailers. Retail stock rotation ensures that consumers always get cereal at peak freshness. The shelf life of cornflakes is typically several months when stored in a cool, dry place, thanks to the low moisture content and protective packaging. Beyond the basic process, Kellogg's has invested in continuous improvement and technological innovation in its plants. Automation now allows for real-time monitoring of every parameter, from the temperature inside the toasting oven to the precise thickness of flakes coming off the mill. Data analytics can flag trends before they become defects, enabling preventive adjustments. Energy efficiency measures such as heat recovery from ovens and optimized air handling systems have been integrated into many plants to reduce environmental impact. Cheerios production begins long before the famous little toasted oat rings take shape on the factory line. It starts with selecting the right oats because in a product like Cheerios, where oats are the star ingredient, the raw material defines the flavor, texture, and nutritional profile. The oats are sourced from farms that grow specific varieties of whole grain oats prized for their uniform kernel size, high beta-glucan content, and consistent milling performance. These farms are often located in cooler climates where oats thrive, and the crops are harvested, cleaned, and transported in bulk to the manufacturing plant under strict quality control conditions. When oats arrive at the facility, they are unloaded into massive storage silos equipped with aeration systems to maintain dryness and prevent spoilage. Before being accepted into the main storage bins, the oats pass through mechanical cleaning systems. These systems remove dust, small stones, and plant debris using vibrating screens, air aspiration units, and magnetic separators that capture any trace of metal contamination. Every incoming lot of oats is also tested in the plant's quality control lab for moisture content, protein level, microbial safety, and the absence of unwanted residues. The next step is oat milling. In the Cheerios process, oats must be transformed from raw groats into a workable form for extrusion. This begins with dehulling, which removes the outer husk from each oat kernel. The cleaned oats are fed into impactor hullers, where centrifugal force cracks the hulls without damaging the inner groats. The hulls are separated from the groats using aspiration and gravity tables, and the groats proceed to a kiln for heat stabilization. Heat stabilization is a controlled toasting step in which the groats are gently heated to deactivate enzymes that can cause rancidity. This step also enhances the nutty flavor of the oats. From there, the groats are rolled or ground into oat flour. for Cheerios, a blend of whole oat flour and sometimes additional grain flours like cornstarch or wheat starch is used to create the right dough properties for extrusion. The oat flour is measured precisely, and minor ingredients such as sugar, salt, and a vitamin mineral premix are prepared in separate dosing hoppers. All these dry ingredients are fed into a pre-mixing system where they are blended into a uniform mix before moving to the wet mixing stage. Wet mixing takes place in an industrial preconditioner or mixer where water and sometimes steam are added to the dry mix. This creates a damp, pliable dough. The ratio of water to dry mix is carefully controlled because it determines how the dough will behave in the extruder. Sensors inside the mixer continuously measure dough temperature, moisture, and homogeneity. This hydrated dough is conveyed immediately into the heart of the Cheerios process, the extrusion system. Cheerios are made using a rotary die extruder. The dough is fed into the extruder barrel, where rotating screws knead and compress it under controlled heat and pressure. The barrel is divided into zones, each with a specific temperature and mechanical shear setting. As the dough moves forward, the heat and pressure partially cook the starches and gelatinize them, creating a texture that will puff slightly when released from the die. At the end of the barrel, the dough is forced through a die plate that has hundreds of tiny, ring-shaped openings. Each opening has a small pin in the center, creating the hole of the Cheerio as the dough extrudes around it. As the dough emerges from the die, it is cut to size by high-speed rotating knives mounted just outside the plate. The freshly cut rings are soft, warm, and slightly expanded. These rings now enter the drying and toasting stages. First comes the primary drying conveyor, where warm air is blown over the pieces to reduce moisture and prevent sticking. After this initial drying, the Cheerios are transferred to large, continuous toasting ovens. These ovens operate with multiple temperature zones. In the early zones, moisture is driven off steadily, and in the later zones, higher heat creates the light brown toasted color and enhances the flavor through Maillard reactions. The toasting step is critical for the signature crunch of Cheerios. Moisture sensors and color cameras monitor the product as it travels through the oven, and computer-controlled adjustments are made on the fly to keep the output consistent. After toasting, the Cheerios must be cooled before packaging. They move along cooling conveyors where filtered ambient air is circulated. The goal is to bring the product to a stable temperature so condensation will not form inside the packaging. This also allows the texture to set fully. In some varieties, a light coating of sugar syrup or flavoring may be applied at this stage using a rotating drum or tumbler. But for classic plain Cheerios, no additional coating is added after toasting. Next, the cooled cereal is sifted to remove small fragments or broken rings, which are collected for use in other applications or for animal feed. The main product stream passes through a final quality control system that includes metal detection, weight checks, and sometimes optical sorting to ensure that every piece is intact and meets size specifications. Samples are pulled for sensory evaluation, which includes tasting for flavor, checking crunch, and verifying that the shape and color meet the brand standard. Packaging begins with precise weighing. Multi-head weighers dispense exact amounts of cereal into form-fill-seal bagging machines. In the classic box format, an inner bag is formed from a roll of plastic film, sealed at one end, filled with cereal, and then heat sealed at the top. Automated arms place the sealed bags into pre-printed cardboard cartons. Each carton is glued shut and stamped with a lot code that contains information about the date, time, and line of production for traceability. These cartons travel along conveyors to case packers, where machines arrange them into corrugated shipping cases. The cases are sealed, labeled, and then stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability during shipping. Finished pallets are stored temporarily in a distribution warehouse with temperature and humidity controls to preserve product freshness. From the distribution center, the pallets are loaded into clean, dry transport trucks and shipped to retailers nationwide. Retail stock rotation ensures that older product is sold first, keeping Cheerios at their optimal freshness for consumers. The shelf life of Cheerios is generally several months due to their low moisture content and protective packaging, but quality is highest in the weeks immediately after production. Throughout the entire process, food safety and quality assurance are paramount. The factory environment is designed for easy cleaning and sanitization with enclosed systems that protect the product from airborne contamination. Employees follow strict hygiene protocols, including wearing hairnets, gloves, and uniforms, and undergoing regular training in food safety practices. Many parts of the plant operate under hazard analysis and critical control points plans, ensuring that every stage, from raw grain to finished package, is monitored for safety risks. Cheerios production is also heavily automated, with control systems tracking hundreds of variables in real time. Data on dough moisture, extrusion pressure, oven temperatures, and packaging line speeds is logged continuously. This allows operators to detect subtle deviations and correct them before they impact the final product. Over the years, the efficiency and precision of Cheerios manufacturing have improved dramatically through advances in automation, ingredient handling systems, and real-time quality monitoring. The making of Frosted Flakes begins with one key ingredient: corn, but not just any corn will do. The factories that produce Frosted Flakes work with carefully selected varieties of yellow dent corn that have the right starch composition, kernel size, and moisture profile to create large, uniform flakes with a crisp bite. These corn varieties are grown in regions where climate and soil conditions produce consistent, high-quality harvests. Before a single load of corn is accepted, it must pass rigorous inspections for moisture content, kernel integrity, absence of mold or mycotoxins, and overall cleanliness. This ensures that, from the very start, the product's signature taste and texture are protected. The corn arrives at the plant in bulk trucks or rail cars and is unloaded into massive storage silos. These silos are fitted with aeration systems that keep the grain cool and dry to prevent spoilage. Before the corn can be stored, it is cleaned using a series of mechanical processes. Vibrating screens remove large debris, aspirators blow away dust and lightweight particles, and magnets capture any stray bits of metal that may have entered during harvesting or transport. After cleaning, the corn is weighed using bulk scales, allowing the plant to track exactly how much raw material will be processed into Frosted Flakes. Once the corn is ready for production, it is first conditioned. Conditioning involves soaking or steaming the kernels to bring their internal moisture to an optimal level for cooking. This step softens the kernels and helps them absorb flavors more evenly later in the process. The conditioned corn is then fed into massive rotary pressure cookers. In these cookers, the kernels are tumbled slowly while being injected with live steam under pressure. A syrup blend of sugar, malt flavor, and a pinch of salt is added, infusing the corn with a sweet, malty taste that will deepen during toasting. This cooking stage gelatinizes the starch inside the kernels, transforming them from hard grain into a tender, flavor-packed base. When the cooking cycle is complete, the hot softened corn is discharged onto cooling conveyors where fans blow ambient or slightly cooled air over the kernels. This halts the cooking process and stabilizes their texture. At this point, the kernels still contain too much moisture to be flaked properly. They move into large industrial dryers, either drum-style or fluidized bed designs, that gradually remove water until the kernels reach the precise moisture level needed for flaking. The drying process is tightly controlled because too much drying will cause the flakes to crumble, while too little will cause them to smear or tear during rolling. After drying, the corn undergoes tempering. This step involves holding the kernels in large bins for several hours to allow the remaining moisture to distribute evenly throughout each kernel. Tempering ensures uniform flaking and helps prevent uneven toasting later. Gentle agitators or slow-moving conveyors in the bins keep the kernels from clumping together while promoting even airflow. Now comes one of the most important steps in the frosted flakes process: flaking. The tempered kernels are fed into massive flaking mills where pairs of enormous, precision-ground steel rollers press each kernel flat in a single pass. The rollers are often water-cooled internally to prevent heat buildup, which could cause sticking or premature cooking. The gap between rollers is adjusted with extreme precision to produce flakes of consistent thickness. This thickness is critical. It determines how the flakes will toast, how they will break in the mouth, and how long they will stay crisp in milk. Freshly flaked corn is pale, soft, and flexible, so it immediately enters long toasting ovens. These are continuous conveyor ovens with multiple heating zones. In the early zones, hot air drives off remaining moisture, locking in the flakes' shape. In the later zones, higher heat brings out the golden brown color, deepens the flavor, and crisps the texture. The toasting stage is also when much of the sweet, roasted aroma is developed. Sensors throughout the oven monitor moisture levels and color, and adjustments to temperature and conveyor speed can be made instantly to keep every batch consistent. Once the flakes are perfectly toasted, they are cooled on open-air conveyor belts to stabilize their structure. This cooling step also prepares them for the next stage that gives frosted flakes their name: sugar coating. The cooled flakes enter large, rotating tumblers known as coating drums. Here, a warm sugar syrup is sprayed onto the flakes in a fine mist. The syrup is made from refined sugar dissolved in water and heated to the right viscosity so it coats evenly without soaking the flakes. As the flakes tumble, every surface becomes covered in a thin, glossy layer. The amount of syrup applied is carefully measured to achieve the brand's signature sweetness without overpowering the cereal's natural corn flavor. After coating, the flakes pass through another drying system, often a warm air tunnel, which removes excess moisture from the syrup and crystallizes the sugar onto the flakes' surfaces. This creates the sparkling, crunchy coating that stays intact until the cereal is submerged in milk. The drying time and temperature are crucial. Too short and the sugar will be sticky. Too long and it may over-caramelize. Following coating and drying, the cereal undergoes final quality checks. It is sifted to remove broken flakes and small sugar granules. The main product stream passes through metal detectors and sometimes X-ray scanners to ensure there are no foreign materials. Samples are pulled regularly for moisture testing, color analysis, sweetness measurement, and texture evaluation. Taste panels may also evaluate random samples to confirm flavor consistency. The finished frosted flakes are then ready for packaging. The cooled flakes are conveyed to multi-head weighing machines that dispense exact portions into high-speed packaging lines. For the classic box format, an inner bag is formed from a continuous roll of food-grade plastic film, sealed at the bottom, filled with cereal, and then heat-sealed at the top. The sealed bag is automatically inserted into a pre-printed cardboard carton. The carton is glued shut, stamped with a production code for traceability, and checked by sensors to ensure it is properly sealed. From here, the cartons are conveyed to case packing machines, where they are grouped into corrugated shipping cases. These cases are sealed with adhesive tape or hot glue, labeled with batch information, and stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability during transit and stored in a climate-controlled warehouse until they are shipped. Every step of the frosted flakes process takes place in a facility designed with strict food safety controls. Air handling systems keep dust and contaminants out of production zones, while stainless steel surfaces are regularly cleaned and sanitized. Automated clean-in-place systems wash the interior of cookers, dryers, and coating drums without dismantling the equipment. Workers wear protective clothing, hairnets, and gloves, and they follow hygiene protocols to prevent contamination. Once the product leaves the factory, it travels to distribution centers, then to retailers. Stock rotation at the store level ensures that consumers get fresh product with the sugar coating intact and the flakes as crisp as they were on the day they were made. Proper storage, cool, dry, and away from direct sunlight, keeps frosted flakes in peak condition for months. Behind every box of frosted flakes is a tightly controlled sequence of thermal, mechanical, and chemical transformations. From the high-pressure steam cooking that gelatinizes the starch, to the precise flaking that creates the perfect surface for sugar adhesion, to the final toasting that seals in crunch and flavor, every step is engineered for consistency. This is why a bowl of frosted flakes tastes the same, whether it was made in Michigan, Canada, or halfway across the world. Each roll of Smarties contains exactly 15 tablets, pastel discs that weigh less than a gram each, yet hold their shape so perfectly they can survive being dropped, shaken, or sat on without crumbling. They're smooth, chalky, lightly tarred, and almost impossibly consistent. And behind that simplicity lies a candy production process that's surprisingly loud, dusty, and engineered to run with near zero waste. Smarties have been made the same way since 1949, when Edward D., a candy maker from England, moved to New Jersey and converted old pellet-making machines, designed for pharmaceuticals, into candy presses. The process still relies on compression rather than cooking. No baking, no melting, no pans of hot sugar. Just dry ingredients, blended and compacted under tons of pressure to form a candy that's hard, smooth, and somehow melts on your tongue. Everything starts with the powder blend. The recipe includes dextrose, citric acid, calcium stearate, and natural or artificial flavorings. Dextrose is the main component. It's a fine, sweet sugar derived from corn that dissolves quickly and gives Smarties their rapid, melt-in-the-mouth texture. Citric acid is what provides the sharp, fruity tang in each flavor. Calcium stearate acts as a flow agent, keeping the powders from clumping or sticking to the equipment. The flavorings and colors are added in carefully measured amounts, each one blended separately depending on the final color of the tablet. Each flavor, orange, pineapple, cherry, strawberry, grape, is mixed in massive stainless steel blenders that can hold hundreds of pounds of dry ingredients at a time. The powders look like soft pastel flour, tinted gently with color: pink for cherry, yellow for pineapple, purple for grape. These mixes are sifted to remove any lumps or foreign particles, and then loaded into holding bins above the compression line. From there, gravity takes over. The powdered candy blend is funneled into the hoppers of rotary tablet presses, machines originally designed for pressing pills. Each press consists of a rotating table filled with die cavities and a set of punches, upper and lower, aligned above and below each die. As the table spins, the punches descend and compress the powder into hard, compact tablets. No heat is used. It's purely mechanical force, tens of thousands of pounds per square inch, pressing each candy into shape. These presses are fast. A single machine can produce thousands of Smarties per minute, each tablet formed in a fraction of a second. You can hear the click-thump rhythm of punches landing hundreds of times per minute, echoing through the factory floor. The speed and pressure must be perfectly calibrated. Too much force, and the tablets crack. Too little, and they crumble in the wrapper. As the tablets are formed, they're immediately ejected onto a conveyor belt and sent to inspection. They travel under high-speed cameras and laser counters that check for missing pieces, size irregularities, and color consistency. Broken or chipped tablets are blown off the belt with puffs of air and collected for reprocessing, ground back into powder and reintroduced into the mixing stage. The flawless tablets continue down the line to wrapping, Smarties are famously packaged in tight rolls of 15, wrapped in clear, crinkly plastic with twisted ends. That roll is another engineering feat. To begin, the candies are grouped by a gating system, mechanical paddles that count out exactly 15 tablets per drop. These tablets slide into plastic film that's being unspooled from a massive roll, moving in perfect sync. A forming collar wraps the film around the candy stack, and heat-sealing jaws bond the film edge. Mechanical fingers twist both ends of the roll, like twisting a piece of taffy at speeds fast enough to blur. It all happens without stopping. The wrapping line moves continuously, synchronized to the tablet press output. If the press slows down, the wrapping slows. If a jam occurs, say a tablet gets stuck in the chute, a robotic sensor stops the whole line within milliseconds to prevent damage or miswraps. Each finished roll is shot into a collection bin where it joins thousands of others for boxing. Depending on the final destination, Smarties rolls are packaged into retail bags, bulk boxes, or specialty gift packs. High-speed cartners scoop up rolls by the dozens and drop them into pre-folded boxes. Every package is weighed, sealed, and labeled with batch information so it can be traced back through every step of the process. But the real complexity of Smarties lies in how clean and controlled the whole system has to be. The powder used to form the tablets is extremely fine. Think baby powder consistency. Left unchecked, it can coat machines, gum up sensors, and create safety hazards. So Smarties factories use powerful vacuum systems that run continuously, pulling excess dust from the air and cycling it through filtration. Workers wear coveralls, gloves, and hair nets, and their shoes go through cleaning stations at every doorway. Even the air itself is managed. Humidity is a constant enemy in tablet candy production. If the air is too moist, the powders clump and stick. If it's too dry, static electricity builds up, which can cause inconsistent fills or attract dust to equipment. Climate control systems run year-round, keeping the production floor within a very narrow range of temperature and humidity. Every major ingredient bin is sealed and vented. The room is positively pressurized so that outside air can't drift in. And then there's flavor. Even though each Smartie is tiny, the flavor has to be concentrated and consistent. That means flavoring oils and acids must be measured down to fractions of a percent. The blending process is carefully timed. Too short, and the flavors don't distribute evenly. Too long, and the powders heat up from friction, which can cause off notes in the final candy. Each batch is taste tested during production, with sample tablets pulled from the press and dissolved in water to measure acid levels and flavor balance. And every flavor gets its own dedicated line or cleaning cycle. Because Smarties are so small, it only takes a few stray tablets to contaminate the color or taste of another batch. Between flavors, the tablet presses are completely disassembled, dies and punches removed, hoppers cleaned, dust vacuums run, and sensors wiped down. The turnaround is fast, but thorough. It's part of what lets Smarties keep their signature clarity in both flavor and color. Quality control doesn't stop with production. Once rolls are packaged, random samples are pulled from each batch and subjected to stress tests. Boxes are dropped, crushed, and shaken to simulate shipping conditions. Rolls are unwrapped and counted to confirm the exact number of tablets. Tablets are measured for diameter, weight, and break strength. And in one test, machines apply pressure from above to see how much force it takes to snap a Smartie. If it breaks too easily, the press calibration is adjusted. And yet, for all this precision, there's almost no waste. Smarties is a closed-loop operation. Any chipped tablets are recycled into powder. Any overfilled rolls are rewrapped. Even rejected wrappers and cardboard from the packaging floor are collected, shredded, and sent to recycling. The factory hums with quiet efficiency. Nearly everything that enters the system leaves as a sellable product. The result is a candy that hasn't really changed in decades, not because it couldn't, but because it doesn't need to. The pastel colors, the slight tartness, the crinkly wrapper, it all adds up to something nostalgic, efficient, and deeply engineered. And what makes Smarties different from other candies is how much is done without cooking. There's no molten sugar, no caramelization, no frying or tempering. It's all compression and control. The candy press is the heart of the process, a machine originally built for medicine, reimagined for sweetness. It doesn't just make Smarties fast, it makes them identical every single time. Jolly Ranchers are some of the hardest candies on earth. Literally, they're engineered to resist biting, built to last, and packed with so much concentrated flavor that a single piece can keep your mouth watering for 10 minutes straight. But behind each brightly colored lozenge is a high-temperature, high-speed process that turns molten sugar into razor-sharp glass with a fruit flavor punch. From raw ingredients to individually wrapped pieces, making a Jolly Rancher is a mix of thermodynamics, timing, and some very sticky science. It starts with just 3 main ingredients: corn syrup, sugar, and flavoring. Sounds simple, but the balance between those first 2 is critical. Sugar gives Jolly Ranchers their sweetness and structure. Corn syrup prevents crystallization and keeps the final product smooth and transparent. Too much sugar and the candy becomes grainy. Too much corn syrup and it won't harden properly. These 2 syrups are pumped into massive stainless steel mixing tanks, each one big enough to hold hundreds of gallons. Here, the sugar and corn syrup are blended together into a thick, pale slurry. Industrial agitators keep the mix moving constantly to prevent any settling or clumping. Once blended, the mixture is heated to over 300 degrees Fahrenheit in a continuous cooker, a machine that looks like a long metal tube wrapped in insulated coils. This step is where everything starts to change. As the temperature climbs, water begins to boil off rapidly. The mixture thickens, darkens slightly, and takes on a glossy sheen. Steam rises from the cooker vents, carrying with it the warm, sweet smell of caramelizing sugar. But unlike caramel, which cooks lower and browns more, Jolly Ranchers are heated just high enough to reach the hard crack stage, between 300 and 310 degrees Fahrenheit, without burning. At this point, the sugar solution becomes incredibly viscous, almost like hot lava. This is candy glass, brittle, shiny, and ready to snap once cooled. The key here is moisture removal. To get the signature glass-like hardness, the mixture must be almost completely dry, less than 2% moisture. That's why the heat is so high and why it's applied so precisely. Even a 1% change in moisture content can mean the difference between a rock-solid candy and a chewy, sticky mess. Vacuum cookers are often used in later stages to finish the dehydration process without overheating the syrup. Once the syrup hits the right consistency, it's ready for flavoring and coloring. But here's the trick: it's still blazing hot, too hot for delicate flavor compounds to survive. So the liquid is transferred to a cooling table or chilled mixing drum, where it's gently agitated and allowed to cool just enough, usually down to around 275 degrees Fahrenheit, before the flavor oils and food coloring are added. This is where things get intensely aromatic. Cherry, watermelon, green apple, grape, and blue raspberry, the iconic Jolly Rancher lineup, all rely on custom flavor blends that are surprisingly concentrated. Just a few drops per batch are enough to infuse thousands of pieces. As the oils hit the warm candy, they vaporize slightly, creating a wall of scent. Workers in this area often wear filtered masks, not because the vapors are dangerous, but because the smell is so overwhelming it can linger for hours. After flavoring, the mixture is ready to be formed, but it's still thick and sticky, like honey that's been left in the sun. At this stage, it's called the rope. The candy mass is loaded into a pulling machine, where it's kneaded and stretched in long, glossy strands. Pulling introduces tiny air bubbles and gives the candy a smoother texture and slightly lighter color. But for Jolly Ranchers, this step is minimal. They're meant to be clear and dense, not fluffy like taffy. So the pulling is short and precise. Next, the rope is fed into a forming machine. A set of calibrated rollers and dies that shape the candy into the familiar oblong lozenges. The rope passes through the rollers, which press it into molds spaced at exact intervals. Each cavity forms a single piece, cutting and shaping at the same time. The machine must keep pace with the candy's cooling curve. Too slow and the candy hardens before it's molded. Too fast and it deforms or sticks. Timing here is everything. The forming rollers run in perfect sync with the pulling speed, adjusting automatically to changes in viscosity. If the candy cools too much, the rope is reheated slightly by overhead lamps or heat plates to keep it pliable. If it's too hot, fans kick on to speed the cooling. Every second matters. Jolly Rancher syrup can go from soft to rock hard in under 10 seconds if left alone. Once formed, the individual candies ride a conveyor through a cooling tunnel. This tunnel is about 40 feet long and packed with chilled, filtered air. The candies must be cooled evenly and gradually to avoid developing internal stress, which can cause cracks or fractures later. As they travel, they harden into solid, glossy lozenges with a smooth surface and near-perfect transparency. Now comes the wrapping, arguably the most technical step of the entire process. Each Jolly Rancher is wrapped individually in a special double-layer film, waxed inner paper and a colourful printed outer film. This wrapping isn't just for branding, it's engineered to withstand extreme stickiness. Even at room temperature, Jolly Ranchers are hygroscopic. They absorb moisture from the air, which can make them tacky. The wax coating on the inner wrapper prevents the candy from fusing to the packaging, while the outer layer protects it from humidity, heat, and light. To apply the wrapper, high-speed flow wrappers align the candies with rotating belts and cutting jaws. The film is cut to size, curled around each piece, and sealed with a heated crimper that twists the ends. These machines can wrap hundreds of candies per minute. So fast, the wrapped pieces look like a blur as they shoot off the end of the line into bins. At this point, the candies are cool, hard, and shelf-stable, but not yet ready to ship. They're sent through a final inspection system that uses cameras and weight sensors to catch malformed pieces, missing wrappers, or empty wrappers, accidentally sealed with no candy inside. Faulty units are kicked off the line with air jets and sent to a reclaim station where wrappers are stripped and the candy is remelted. The good batches move on to packaging. Depending on the final format, Jolly Ranchers are dropped into bags, jars, or boxes. For fun-size packs, robotic arms count out a set number of wrapped candies, funnel them into plastic pouches, and seal the tops. For bulk jars, conveyors load hundreds of candies into plastic tubs, which are then lidded and shrink-wrapped. Every unit is batch-coded, dated, and weighed, and all of this happens under a strict quality protocol. If a single bag in a batch fails a weight or seal check, the entire batch is flagged for inspection. Behind the scenes, data flows constantly. Sensors track temperature at every stage, from syrup cooking to cooling tunnel exit. Viscosity is monitored in real time. Belt speeds, humidity levels, room temperature, and even air particle counts are logged. Operators monitor it all from control stations with touchscreen dashboards, ready to tweak parameters at a moment's notice. And the environment must be spotless. Sugar dust is a serious hazard in industrial settings. It's flammable, sticky, and a magnet for bacteria. So the production floor is kept under positive pressure, filtered continuously, and cleaned at the end of every shift. All machines are made with smooth, food-grade steel and designed to disassemble quickly for daily sanitation. What's perhaps most fascinating is how scalable the process is. The same basic steps: cook, flavor, form, cool, wrap, apply whether a facility is making 10,000 pieces an hour or 10 million. Everything is modular. Need to make more watermelon? Operators adjust the flavor tanks and swap in a red dye cartridge. Need to make heart shapes for Valentine's Day? change the mold plates on the forming rollers, and recalibrate the wrapping alignment. And because Jolly Ranchers are made from a solid sugar glass base, they have an almost indefinite shelf life, up to 18 months with no preservatives. That makes them ideal for long shipping routes, hot climates, and bulk packaging. It's also why they're so popular as party favors, parade tossers, vending machine fillers, and Halloween staples. But at the core of every piece is that glassy crunch, that hard, smooth texture that doesn't yield until the very end. It's not just candy, it's carefully crafted sugar architecture. The entire process is designed to preserve that structure, from the moisture level in the cooker, to the cooling curve on the conveyor, to the twist in the wrapper. In the high output production of Coca-Cola, the process is defined by continuous motion, absolute precision, and the seamless choreography of ingredients, machines, and packaging systems that transform individual raw components into millions of finished beverages every single day. The process begins deep within the mixing facility, where highly purified water, stripped of all minerals, chemicals, and organic material through a series of activated carbon filters, deionization beds, and ultraviolet treatment chambers, forms the foundation of the beverage. This purified water, tested continuously for pH, conductivity, and microbial presence, is stored in stainless steel tanks where it awaits dosing. Simultaneously, concentrated syrup, pre-mixed to exact proportions in controlled rooms, is pumped from insulated holding tanks through jacketed pipelines that maintain a constant temperature to prevent any crystallization or viscosity shifts. These lines carry the syrup to the blending system, where the water and concentrate meet inside high-speed mixing chambers fitted with vortex turbines that spin at thousands of revolutions per minute. These turbines ensure that every drop of syrup disperses evenly throughout the water stream, achieving uniform flavor concentration at massive scale. Inline refractometers measure sugar content and density in real time, adjusting flow valves to keep the bricks level within fractions of a percent of specification. Once blended, the now recognizable but uncarbonated Coca-Cola base enters a chilling loop, where it is passed through plate heat exchangers that rapidly drop the temperature to just above freezing. This cooling is critical because carbonation requires both precision and cold liquid. Warmer temperatures reduce the solubility of carbon dioxide, and the beverage must be stabilized before the gas is introduced. The chilled liquid is then sent to the carbonation unit, a sealed pressurized chamber where CO2 is injected under precise pressure and temperature control. The carbon dioxide gas, stored in liquid form in cryogenic tanks, is vaporized and filtered before injection, ensuring purity and taste neutrality. As the CO2 is forced into the beverage under pressure, it dissolves instantly, and the resulting mixture, now fully carbonated Coca-Cola, is routed into buffer tanks, where it is gently agitated to maintain consistency and avoid foaming. These tanks are under positive pressure to prevent degassing, and every line is monitored for CO2 saturation, temperature drift, and fill levels. From these tanks, the carbonated beverage moves directly to the filling lines, which operate with unbroken efficiency, handling thousands of bottles or cans per hour with mechanical repetition and minimal tolerance for variation. For bottles, the first step begins with preforms, small plastic tubes made of PET, fed from hoppers into a rotary oven where they are heated to a malleable state, then transferred into a blow molding carousel. Inside this machine, each preform is stretched and inflated with high-pressure air into the shape of a bottle inside precision-machined metal molds. The formed bottles are immediately cooled, trimmed, and transferred onto conveyors that carry them upright toward the filling line. Throughout this path, they remain untouched by hands and isolated from ambient air by enclosed systems that maintain sanitary conditions. As they approach the filler, the bottles are inverted and rinsed internally with sterile air or ionized water to remove any particles. They then pass under the filling heads, nozzles that lower into the neck of each bottle, creating a tight seal and filling them under counter-pressure conditions to prevent foaming or CO2 loss. The entire filling cycle for each bottle takes only a few seconds, monitored by laser-level sensors that detect exact volume. As each bottle fills, the flow is throttled to avoid turbulence, and the gas pressure is equalized to maintain carbonation stability. Immediately after filling, the bottles are transferred to the capping station, where precision-guided turrets place caps onto each one and tighten them with calibrated torque drivers. The caps themselves are fed from vibratory bowls that align them correctly and move them through high-speed chutes. As each bottle is capped, it is passed through a vacuum checker that detects seal integrity by measuring internal pressure, and any container that doesn't meet the threshold is automatically diverted from the line. In parallel to bottle filling, can production follows a similarly synchronized path. Aluminum cans arrive already formed, stacked, and nested, and are depalletized in towers that feed them one by one onto high-speed conveyor belts. These cans move through a rinse tunnel where jets of deionized water clean the interiors. Then dry blowers remove every drop before they reach the filler. Because cans can't be sealed under counter-pressure like bottles, they are filled with a slightly different method. First purged with carbon dioxide to displace oxygen, then rapidly filled with cold, carbonated Coca-Cola, and finally topped with lids while still under pressurized gas. The lid seamer seals each can by curling the edge of the aluminum lid around the lip of the can body and compressing it tightly with a roller under immense force. The seam is inspected by cameras and load sensors, and every few hundred units, samples are removed automatically and sent to inline X-ray or cutaway analysis to ensure structural integrity. Once sealed, the cans are dried again, passed through a date coder that prints production codes and batch identifiers directly onto the lid, and then sorted into lanes based on packaging format: single, multi-pack, or bulk tray. Now fully sealed, bottles and cans alike move toward labeling and secondary packaging. Bottles pass through shrink sleeve or wraparound labelers that align each container using optical sensors before a printed film sleeve is applied and shrunk into place using steam or infrared tunnels. Can multi-packs are grouped into clusters by mechanical pusher arms and wrapped in printed film or placed into cardboard carriers. Robotic arms lift and arrange finished units into cartons or trays, depending on regional packaging standards, and automated check weighers confirm product count and configuration within each package. After secondary packaging, the products move to palletizing stations. Here, robotic stackers use vacuum grippers or clamp heads to build pallets layer by layer, rotating and interlocking packs to maintain balance and optimize density. Slip sheets or corner boards may be inserted for additional stability. Once complete, each pallet enters a rotary stretch wrapper, where clear plastic film is wrapped under tension around the stack, binding it tightly to protect against vibration or shifting during transport. A thermal label is printed and applied to the outer film, displaying destination, pallet ID, and manufacturing metadata. Every part of the line, from syrup mixing to final wrapping, is connected to a centralized control system, often SCADA-based, which aggregates data from thousands of sensors across the production floor. It tracks real-time flow rates, fill volumes, pressure changes, CO2 consumption, label placement accuracy, packaging efficiency, and quality checkpoints. Alerts are triggered the moment a parameter deviates from its programmed limits, prompting either automatic correction by servo-driven actuators or shutdown protocols to isolate the issue for inspection. Quality assurance is deeply embedded into the process. Sample bottles and cans are pulled at regular intervals by robotic pickers and sent to adjacent quality labs, where automated instruments test for bricks levels, carbonation volume, pH, color density, and turbidity. Gas chromatographs may analyze flavor profile consistency, and oxygen analyzers confirm shelf life integrity. Retention samples are archived from each production batch in cold storage, enabling full traceability in case of future inquiry. Cleaning-in-place systems activate between flavor runs or at set intervals, flushing pipes, tanks, and filling valves with heated caustic solutions, followed by acid rinses, and finally with purified water. All internal product contact surfaces are sanitized, and the data logs are updated with each wash cycle. This ensures the system is sterile before the next production batch begins, whether it's more Coca-Cola or a different product line altogether. All along the line, mechanical timing is critical. Bottles that arrive milliseconds too soon or too late can cause backup or collision, so every machine is programmed to respond to product flow, spacing, and acceleration. Timing screws, sensors, and motorized star wheels maintain precise positioning, and buffer conveyors absorb temporary surges without stopping the line. Overhead, cameras and inline vision systems inspect every package for branding alignment, color accuracy, seal integrity, and tamper evidence, discarding any product that fails visual QA. From a distance, the system appears to operate like a single, unified machine. Syrup, water, gas, packaging, and automation all working as one organism, never pausing, never deviating. Every bottle and every can moves through this stream of equipment with exacting control, shaped not by hand, but by air pressure, centrifugal force, liquid dynamics, and heat energy, and by the software that orchestrates it all behind the scenes. The production of cherry Coca-Cola begins with the coordinated movement of ingredients through a tightly integrated system of tanks, pipes, mixers, fillers, and control panels, where every second of the process is timed, and every variation in flow, pressure, or temperature is monitored and corrected in real time. The defining element of this beverage, the distinct cherry-flavored profile, requires its own set of ingredients to be introduced at specific intervals within a continuous fluid stream, and the entire operation is driven by automation that ensures each bottle or can delivers the same flavor, carbonation, and experience without deviation. At the heart of the operation lies the mixing zone, a sealed chambered area of the factory where the formulation begins, not with bottles or packaging, but with the controlled blending of ultra-purified water and concentrated syrup. The water itself is subjected to a multi-stage filtration process that removes every mineral and contaminant through reverse osmosis membranes, UV sterilization lights, activated carbon beds, and deionization columns. The final water output is chemically neutral, consistent in temperature, and free of flavor interference, ensuring it will not alter or dull the delicate cherry infusion that characterizes the product. Simultaneously, the cherry Coca-Cola based syrup is prepared in mixing tanks where measured amounts of sweeteners, flavor agents, acidity regulators, and natural cherry extracts are combined into a thick, dark syrup with precise viscosity. Each batch is homogenized with high-speed impellers, continuously monitored for density using inline refractometers, and sampled through sterile taps for real-time verification of its sugar content, aroma, and visual clarity. Once verified, the syrup is stored in insulated holding tanks fitted with agitators to prevent settling and ensure uniformity prior to dosing. When the purified water and cherry-infused syrup are combined, they are fed into high shear blending, chambers where specially engineered turbines swirl the mixture at controlled speeds to ensure total integration. These blending units include flow regulators that adjust the syrup to water ratio down to tenths of a percent so that every liter leaving the chamber maintains exact sweetness and acidity levels. This blending is continuous and uninterrupted, forming a central stream of cherry Coca-Cola base that is directed toward the chilling loop. Before carbonation, the mixture is rapidly cooled using a set of plate heat exchangers where cold glycol fluid moves through alternating stainless steel plates, drawing heat from the beverage as it flows in an adjacent channel. The cooling process is essential, dropping the beverage temperature to near freezing, around 0 to 2 degrees Celsius, which allows the carbon dioxide to be absorbed efficiently and held within the liquid under pressure. Once chilled, the drink enters a sealed carbonation unit. Inside this pressurized chamber, carbon dioxide gas, stored in liquid form at cryogenic temperatures, is vaporized, filtered, and then injected into the cold cherry Coca-Cola base through a sparging system that disperses the gas evenly throughout the liquid. The CO2 dissolves into the beverage instantly due to the low temperature and high pressure, and the resulting carbonated drink flows forward to the buffer tanks, where it is gently mixed and held under pressure to prevent gas release or foaming. These buffer tanks act as holding silos between mixing and filling, maintaining consistent temperature and carbonation levels while regulating the supply to each individual filling line. The tanks are fitted with pressure sensors, degassing valves, and agitation paddles that rotate at slow speeds to preserve homogeneity without disturbing the carbonation level. From here, the carbonated cherry Coca-Cola is ready to be dispensed into containers at high speed. If bottles are the intended format, production begins with PET preforms, small test tube-shaped plastics that are loaded into feed trays and passed through a rotating oven chamber fitted with infrared heaters. The preforms are warmed to a pliable temperature before being inserted into steel molds, where compressed air blows each preform into the shape of a bottle within milliseconds. The molds are cooled, and the newly formed bottles are ejected onto conveyor lanes, where they begin their journey to the filling line. Each bottle passes through an inversion unit, where they are turned upside down and rinsed with filtered air or ionized water to eliminate static charge and remove any residual particles. Once cleaned, they are flipped back upright and enter the filling carousel, a large rotating ring with multiple filling heads. As each bottle passes underneath a head, it is sealed airtight and filled using counter-pressure filling. CO2 is first used to purge oxygen from the bottle. Then the beverage is dispensed, equalizing pressure to avoid foaming or gas loss. As the bottle fills, a level sensor determines the precise volume, and flow is shut off with a clean break once the target fill is reached. The next stage is capping. Cap hoppers sort and orient the plastic caps, feeding them down a chute where robotic arms place each cap onto the filled bottle. A torque-controlled spindle tightens every cap to an exact specification, and a vacuum sensor checks that each seal is secure. Each bottle then passes through a high-speed date printer that applies production information, including line number, time code, and expiration date. Can filling follows a similar track, but on a separate line with specialized machinery. Empty aluminum cans arrive pre-formed, palletized, and stacked in tall columns. These stacks are depalletized and fed into the can rinsing tunnel, where they are cleaned with a high-pressure deionized water spray, then dried using high-speed air knives. Cleaned cans are conveyed directly into the filling system, where they pass beneath a gas flush station that replaces internal air with carbon dioxide to maintain freshness. As the cherry Coca-Cola is dispensed into each can, the filling head retracts, and a lid is placed onto the top of the filled can by a precision seamer. This machine uses a dual-action compression and curl technique to lock the lid onto the can body, creating a hermetic seal. Immediately afterward, the can is cleaned again externally, printed with production codes, and passed to the packaging lanes. At this point, both bottles and cans converge into the secondary packaging area, where products are grouped, aligned, and prepared for shipment. Bottles are collected into multi-packs using servo-controlled arms that lift and guide them into shrink film, which is wrapped and sealed around the group before passing through a heat tunnel that shrinks the film tight. Cans are guided into multi-lane collators that align sets of 6, 12, or 24, depending on the package, and apply either shrink wrap or cardboard wraps printed with branding and barcodes. Cameras verify each pack's alignment, color fidelity, and integrity before they are cleared for stacking. Packaged units move toward robotic palletizing systems, where vacuum lifters and grip arms organize them into stable layers, rotating the orientation of each pack to create interlocking rows. Slip sheets are inserted between layers, and once the pallet reaches full height, it is transferred into an automatic stretch wrapper, which encases the pallet with tensioned film from top to bottom. A printed label with barcodes, destination data, and production batch is applied to the outside, and the pallet is transferred to the loading dock for transport. Meanwhile, every single movement on the production floor is tracked by an integrated control system, a network of programmable logic controllers and interface stations that monitor temperature, pressure, syrup ratios, carbonation levels, fill rates, and flow speed. The system adjusts each parameter in real time. If syrup density increases due to ambient temperature, pumps slow fractionally. If bottle alignment drifts off center, the guide rails shift laterally. If carbonation drops even slightly, the gas injector valve pulses at higher frequency until the correct level is restored. Throughout the process, quality assurance teams collect real-time data from sensors and pull physical samples at intervals. These samples are sent to inline labs, where technicians run automated tests using densitometers, CO2 analyzers, pH probes, and colorimeters to ensure each bottle or can meets flavor, appearance, and stability specifications. A taste panel may confirm final flavor consistency before the batch is cleared for release, and a retention sample is archived for traceability. Between batches, the entire system undergoes a clean-in-place (CIP) procedure. Pipes, valves, tanks, and filling heads are flushed with heated alkaline solutions, followed by acidic rinses and sterilization stages. Sensors monitor residue levels in rinse water, and the system will not allow a new batch to begin until cleanliness thresholds are met across the entire line. Inside the production facility dedicated to Coca-Cola Zero, the operation begins with a steady rhythm of systems calibrated to blend, chill, carbonate, and package a product that relies on absolute precision. Because unlike its sugar-sweetened counterparts, Coca-Cola Zero is formulated with no sugar at all, relying instead on an exact balance of non-nutritive sweeteners that must be handled with extraordinary control to maintain both flavor integrity and regulatory compliance. The process begins, not with packaging, not even with carbonation, but with water. Water that has been stripped of every mineral, ion, and microbe through a comprehensive purification chain that includes activated carbon filtration, multi-stage reverse osmosis membranes, ultraviolet sterilization, and final stage polishing filters to ensure that every molecule entering the blend tanks is completely neutral. This water, once purified, is cooled immediately and transferred into a network of stainless steel supply tanks, each one connected to high-flow dosing manifolds, where the Coca-Cola Zero concentrate is introduced. Unlike other formulas, the Coca-Cola Zero syrup contains highly sensitive ingredients that must be mixed with close control over both flow rate and agitation speed. A series of variable speed turbines inside a baffled blending chamber begins to stir, drawing in sweetener concentrates from microdosing pumps which meter out fractions of grams per second, ensuring that every liter of finished product will contain only the approved quantity of aspartame, acesulfame potassium, and other formulation components. The syrup is mixed with chilled, purified water in a continuous loop, constantly circulating through inline density sensors and refractometers that verify every measurable characteristic of the mixture: its Brix equivalent, its acidity level, its color profile, and its consistency. all monitored by SCADA systems that relay performance data to centralized control stations positioned throughout the factory floor. If the syrup becomes too concentrated, water flow is increased fractionally. If any temperature drift is detected in the mixing tank, the coolant jacket is adjusted to compensate instantly. The goal is absolute uniformity. Every second, every drop must match the one before it. As the base liquid moves into the carbonation stage, it passes through a final chilling module where its temperature is brought down to a near freezing range. At this point, the beverage is ready for carbonation. The carbon dioxide gas, stored in its own cryogenically cooled system, is injected into the mixture using a high-efficiency carbonator, a pressurized steel chamber where the CO2 enters under regulated pressure through micro-diffusers, creating billions of microscopic bubbles that dissolve immediately into the cold liquid. The flow of CO2 is continuously calibrated according to beverage temperature, system pressure, and product viscosity, with flow sensors and back pressure valves maintaining stability as thousands of liters pass through each hour. Once fully carbonated, the beverage is routed into pressurized holding tanks, buffer vessels that serve as the final point of quality assurance before the product reaches the filler. These tanks are lined with level indicators, gas traps, and temperature probes, all synchronized to maintain the carbonation level while gently agitating the liquid to prevent stratification or foaming. Here, any final testing is performed in line. Carbonation volume, turbidity, residual sweetness, and pH are verified one last time. A sampling valve allows automated collection of product every few minutes, and that sample is passed directly into a micro lab for flavor standardization analysis using spectrophotometry and gas chromatography. Meanwhile, the packaging line is already in motion. For plastic bottles, the process starts with injection molded preforms, small and thick-walled, which are delivered in bulk and stored in hoppers above the blow molding machines. These preforms descend through a heater array where infrared panels warm them to a precise forming temperature before they are dropped into two-part molds. Compressed air is blasted inside, expanding the plastic against the inner mold walls to create full-size bottles instantly. As the mold opens, cooled air is used to solidify the bottle's shape, and a robotic gripper places each new bottle upright onto a moving conveyor that feeds directly toward the filling station. Before any liquid enters the bottles, they are passed through an inverted rinsing tunnel where ionized air is sprayed inside each one to remove microscopic particles. They continue along the line toward the filler, where a rotary system spins each bottle into place beneath a filling valve. This valve descends into the mouth of the bottle, creates a pressurized seal, and initiates a filling sequence that begins with a brief CO2 purge to eliminate oxygen and preserve shelf stability. The pressurized beverage flows into each bottle in just under 2 seconds, with real-time fill level sensors using laser measurement to verify that each container is consistent to the milliliter. There is no overflow, no foam rise, no turbulence. The pressure balancers are engineered to make the fill seamless and silent. Once filled, the bottles pass immediately to the capping turret. High-speed feeders deliver bottle caps from a bowl sorter into the capping head, which presses each cap onto the threads and twists them into place using torque-monitored spindles. Each cap is verified for application tightness and angle, and a vacuum test is performed at random intervals by an inline tester that verifies the seal by measuring pressure drop inside a chamber. If a cap is misapplied, the bottle is instantly diverted from the line. After capping, the bottles pass through a date and batch printer, which uses thermal inkjet or laser etching to apply identification directly to the neck or shoulder of the bottle, depending on line configuration. In parallel, aluminum cans are prepared on their own dedicated track. Delivered by the pallet, preformed cans are depalletized and sent through a high-speed depuck system that guides them into the line one at a time. Each can passes under a rinse sprayer and then through a drying tunnel before entering the can filler. This equipment is built for volume. Multiple nozzles dispense product simultaneously, filling dozens of cans per second, each one pressurized beforehand to prevent foaming during the rapid fill. A lid is placed on each can immediately after filling, and a seam roller presses the lid onto the body, creating a hermetic seal that is pressure tested, scanned by vision systems, and validated against a standard profile. Cans are printed with batch codes and transferred to the packaging section. Now, both bottles and cans proceed to the secondary packaging area, where multi-packs are created using automated grouping systems. Bottles are collated into clusters of 6, 12, or 24, wrapped tightly in shrink film, and sent through a steam tunnel that shrinks the plastic smoothly around the group without obscuring the labels. Cans are similarly grouped and placed into printed cardboard sleeves or plastic rings, depending on the destination. Each group is weighed, scanned, and inspected for alignment before being transferred into cartons. Carton erectors form boxes from flat stock, fold them automatically, and glue them using hot melt adhesives before they are filled with packs by robotic arms that stack them precisely inside. Once loaded, the cartons are sealed, labeled, and conveyed to a palletizing system where mechanical arms stack them onto pallets in programmed patterns to maximize space and stability. A slip sheet may be inserted between layers, and once the stack is complete, it moves into a stretch wrapper that encases the pallet with plastic film to lock it tight for shipping. The entire pallet is weighed, labeled, and scanned before being queued for loading. M&M's production begins with the manufacturing of the chocolate core. Each milk chocolate center is formed by molding a precise deposit of tempered chocolate onto a cooling belt. Chocolate mass is created by blending sugar with cocoa liquor and milk solids in a high-capacity mixer. This blend is refined through a 5-roll mill that reduces particle size to below 30 microns. The refined paste is moved to conching tanks where it is mixed and aerated at a temperature of 55 degrees Celsius. Lecithin is added as an emulsifier to achieve a smooth, flowable texture. The conched chocolate is held in jacketed tanks to maintain a liquid state. It is tempered using a 3-stage tempering unit which cycles the chocolate through controlled heating and cooling to form stable crystal structures. Tempered chocolate is pumped to a depositor that releases metered drops onto a stainless steel belt moving through a cooling tunnel. The belt temperature is kept between 5 and 10 degrees Celsius to solidify the chocolate in less than 60 seconds. The formed centers are demolded mechanically and stored in buffer bins before the next process. For peanut M&Ms, the process begins by dry roasting raw peanuts in continuous belt roasters. Roasting temperature is maintained at 160 degrees Celsius for 20 minutes. Peanuts are then cooled by ambient air in a vibrating cooler. After cooling, they pass through a sizing unit that removes undersized or broken nuts. The selected peanuts are fed into panning drums where chocolate is applied in successive layers. Each drum rotates at a fixed angle and speed to ensure uniform tumbling. A measured amount of chocolate is sprayed onto the surface of the peanuts using heated nozzles. After each application, cold air is blown into the drum to partially solidify the layer. This process repeats until the peanuts reach a target diameter. The final chocolate coating is smoothed using a polishing pass with minimal chocolate to eliminate surface irregularities. Crispy M&Ms are built around an extruded rice core. Rice flour and corn grits are mixed with water and processed through a twin-screw extruder. The extruded dough is cut into uniform pellets using a rotating blade. Pellets are puffed in a high-temperature expansion chamber. After expansion, they are dried in a convection dryer, then coated with a thin film of fat to reduce moisture absorption. The puffed cores are enrobed in chocolate using the same panning method applied to peanuts. All chocolate-coated centers are transferred to the sugar coating area. The process starts in large rotating pans where the cores are sprayed with a sugar solution. The sugar syrup consists of sucrose water and glucose and is delivered at a constant temperature of 75 degrees Celsius. Each spray cycle is followed by a drying cycle that circulates dehumidified air around the rotating bed of centers. Sugar builds up in fine layers over dozens of cycles. The panning operator adjusts spray volume drum rotation speed and airflow to maintain uniformity. Once the sugar shell reaches the desired thickness, color is applied. Coloring is done by mixing food dye with shellac and carnauba wax to produce a glossy, tinted coating. The colorant is misted onto the sugar-coated centers in a fine spray. Multiple passes may be required for dark colors like red or brown. After coloring, the coated pieces are polished with a dry mixture of shellac and wax. This step is performed in polishing pans, rotating at low speed. The polishing agent adheres to the surface and is distributed by friction between the tumbling pieces. The resulting finish is smooth, hard, and glossy with highlight reflectivity. Polished M&Ms are discharged from the pans and moved to a conditioning silo. This silo is temperature and humidity controlled to allow the coating to fully harden and stabilize. Residence time in the silo is typically 2 to 4 hours depending on coating thickness. After conditioning, the candies are conveyed to the printing station. The iconic letter is applied using offset graver printers. Each piece is positioned in a dimpled conveyor plate with cavities sized to hold one candy. The plate passes beneath a print head which uses edible white ink. The print roller is engraved with the letter M and rotates in sync with the conveyor. Contact pressure is controlled pneumatically to ensure legibility without damaging the shell. Printed candies are inspected by machine vision systems that detect missing or malformed prints. Unmarked units are removed by air jets and recycled into the system for reprinting. Approved units continue to the packaging stage. The candies are weighed and dosed using multi-head combination weighers that drop exact quantities into vertical form fill seal machines. Packaging film is pulled into the forming collar and sealed into a tube. The bottom is sealed with a heated jaw and the product is dropped in. The top seal is then applied, creating a pillow pack. Filled packages are conveyed to check weighers that verify compliance with weight specifications. Any over or underweight packs are removed automatically. From start to finish, the process involves sequential mechanical operations that include mixing, depositing molding panning, spraying printing, and sealing. Each unit operation is tuned to specific parameters that ensure dimensional consistency and coating integrity. The manufacturing line is modular, with separate zones for chocolate handling, core preparation, sugar coating, and final packaging. Mass flow is maintained using belts, pneumatic conveyors, and elevators that transfer product between levels. The entire line is integrated by a control system that monitors temperature, flow rate, viscosity, and speed at each point. Adjustments are made automatically through feedback loops that maintain constant output. There are no batch holds once the system is running. The chocolate centers flow continuously through coating, coloring, and packaging without pause. Sugar solutions are replenished through a bulk feed system with inline heating and mixing. Chocolate is tempered in a loop with real-time viscosity monitoring. Each candy undergoes a transformation that begins with a molten mass and ends with a layered composite structure. The core is solid or puffed depending on type. The first layer is tempered chocolate applied by drum enrobing. The second layer is crystalline sugar formed by sequential syrup application and drying. The third layer is colorant and wax forming the glossy finish. The fourth step is marking with the printed letter. All coating is additive applied in micro-thin layers, controlled by time rotation and fluid volume. There is no molding of the outer shape. The spherical form is achieved through cumulative coating and mechanical tumbling. The smoothness is the result of abrasion polishing and repeated layering under rotation. Thermal inputs are limited to chocolate tempering, syrup heating, and ambient conditioning. No baking, frying, or high temperature processing occurs. Moisture is carefully controlled during sugar coating to avoid bloom or crystallization defects. Every part of the process is dry, except the syrup spray and initial chocolate melt. Mechanical design of the panning drums ensures even exposure for each piece. Drum material is stainless steel with ribbed interiors that increase mixing efficiency. Air delivery systems are connected to each drum to maintain controlled drying. The air is filtered, cooled, and dehumidified before being directed at the product. Timing across the system is synchronized by programmable logic controllers. Every depositor, cutter, printer, and packager is indexed to match upstream flow. Any stoppage triggers a cascading halt to preserve continuity. Materials are buffered at key points to allow restart without waste. Twix production begins with controlled preparation of the biscuit base that defines the structure of the bar. Twix biscuit dough is created by feeding wheat flour into a continuous mixing system. The flour is combined with sugar and vegetable fat inside a horizontal mixer. Mixing paddles rotate at low speed to coat flour particles with fat. Water is added in measured flow to bind the mixture into a cohesive dough. Dough temperature is regulated to maintain firmness during shaping. The mixed dough exits the mixer and enters a feed hopper that supplies the forming line. The dough is transferred onto a rolling table, where compression rollers flatten it into a continuous sheet. Roller gap settings determine final biscuit thickness. The sheet passes through alignment guides that maintain straight edges. A rotary cutting drum imprints the dough into uniform rectangular segments. Excess dough is removed and recycled upstream. The shaped dough pieces are placed onto a steel mesh conveyor for baking. The baking stage uses a tunnel oven with multiple heating zones. The conveyor transports dough pieces through gradually increasing temperatures. Initial zones dry the surface without browning. Middle zones promote internal structure development. Final zones create golden coloration and crisp texture. Oven airflow is directed above and below the conveyor. Baking time is adjusted to control moisture content. The baked biscuit bases exit the oven with stable shape and strength. Freshly baked biscuit bases move directly into a cooling tunnel. Ambient and chilled air flow reduces biscuit temperature. Cooling prevents caramel deformation during later stages. Conveyor speed maintains spacing between pieces. The biscuits emerge cooled and rigid. They are aligned into lanes for caramel application. Caramel production occurs in a separate continuous system. Glucose syrup flows into a preheating chamber. Milk solids and sugar are added under agitation. The mixture passes through a vacuum cooker. Reduced pressure lowers boiling temperature. Moisture evaporates rapidly to thicken the caramel. Cooking parameters define final viscosity. The caramel exits the cooker as a smooth, elastic mass. Cooked caramel is transferred into a holding vessel. Slow agitators prevent crystallization. The caramel is pumped through heated pipes to the depositor. The depositor contains multiple nozzles aligned with biscuit lanes. Each nozzle dispenses a precise ribbon of caramel. Deposition rate controls caramel height. Temperature ensures proper flow and adhesion. Caramel-coated biscuits move through a setting tunnel. Cool air partially solidifies the caramel layer. The caramel becomes firm enough to hold shape. The biscuits continue along the conveyor without distortion. The caramel surface remains tacky for chocolate bonding. Chocolate coating begins with preparation of milk chocolate. Cocoa mass, sugar, milk powder, and cocoa butter are blended. The mixture is refined to reduce particle size. Conching develops smooth texture. Finished chocolate is transferred to tempering units. Tempering controls crystal formation. Chocolate reaches a stable liquid state. Tempered chocolate flows into the enrobing machine. A continuous chocolate curtain forms across the conveyor. Biscuit caramel assemblies pass beneath the curtain. Chocolate coats the top and sides evenly. A bottoming system coats the underside through the mesh belt. Excess chocolate drains back into the system. Air knives shape the chocolate layer. Gentle vibration removes bubbles. The coating thickness becomes uniform. Decorative surface lines may form naturally from airflow. The enrobed Twix bars enter a cooling tunnel immediately. Cooling tunnels use staged temperature zones. Initial zones prevent surface cracking. Later zones fully crystallize the chocolate. Air velocity ensures even cooling. Belt speed defines dwell time. The chocolate shell hardens around the biscuit and caramel core. After cooling the bars, exit with rigid structure. The bars are transferred to the splitting station. Twix bars are cut lengthwise into twin fingers. Servo-controlled blades ensure precise separation. Each finger maintains identical dimensions. Separated Twix fingers are aligned on packaging conveyors. Spacing belts organize the flow. The bars enter flow wrapping machines. Packaging film is fed from large rolls. The film wraps around each finger. Longitudinal seals are formed by heated rollers. End seals are created by rotating jaws. Wrapped fingers are paired for twin pack format. Collation belts bring two wrapped fingers together. The paired unit is wrapped again or inserted into an outer sleeve. Wrapping speed matches upstream production. The sealed packs exit the line in continuous flow. Throughout Twix, manufacturing every step is synchronized. Conveyor speeds coordinate with deposition rates. Thermal stages are sequenced to avoid overlap. Mechanical forming ensures consistent geometry. Material flow remains uninterrupted from dough to wrapper. The biscuit base provides rigidity. The caramel supplies chew and adhesion. The chocolate delivers coating and protection. Each layer is applied in a defined order. Temperature control maintains layer integrity. Timing ensures bonding without deformation. Twix production operates as a linear system. Dough shaping precedes baking. Baking precedes caramel deposition. Caramel setting precedes chocolate enrobing. Chocolate cooling precedes cutting and wrapping. Each stage depends on the previous one. Ingredient transformations are mechanical and thermal. Dough changes through heat exposure. Caramel thickens through evaporation. Chocolate crystallizes through controlled cooling. No stage reverses a previous transformation. The biscuit sheet thickness defines bite texture. Caramel viscosity defines chew resistance. Chocolate thickness defines snap. These variables are adjusted through machine settings. No manual shaping occurs after initial dough forming. Continuous monitoring of belt alignment prevents product drift. Sensors maintain spacing accuracy. Pump pressures control flow stability. Roller speeds define forming precision. Each parameter is linked to output consistency. Twix bars emerge fully assembled before packaging. The layered structure remains intact. The product shape remains constant across units. The manufacturing line produces thousands of bars per hour. Output remains uniform due to synchronized automation. Every Twix bar follows the same physical path.